Hello there, and welcome to Life Beyond Seen, where curiosity drifts gently beneath the surface and science takes the scenic route into the unknown. Tonight's slow and steady journey begins not among the stars or the ticking of a clock, but far closer to home, beneath a vast blue surface that most of us only ever skim. We're heading down, deeper and deeper, into one of the least explored places on Earth. A place so extreme and so remote that sunlight itself never arrives. It is a world that few have seen, and fewer still have truly imagined, and yet it lies right beneath the familiar swells of the Atlantic Ocean. This is the story of the Milwaukee Deep, the deepest point in the Atlantic, a dark, hidden scar at the bottom of the sea that plunges more than 8.5 kilometers into the Earth. It is a place so alien it might as well be another planet. Yet it is here, quietly existing beneath the waves we walk beside every day. Before we set off into that darkness, I'm curious. Where in the world are you listening from tonight? Are you somewhere inland, far from the smell of salt and the cry of gulls, or close enough to hear waves against a shore? Have you ever stood on a beach and stared out toward the horizon, wondering what lies beneath that endless surface? It's a comforting thought, isn't it? That even in a world mapped by satellites and crisscrossed by cables, there are still places so unknown, so untouched, that they remain largely a mystery. If this slow dive into Earth's hidden depths feels like a good way to unwind, I'd be grateful if you'd like the video and subscribe. It helps this little corner of calm find others who might need a quiet moment too. Now, if you're ready, let's begin our descent, because beneath the bright busy skin of the ocean lies a realm where light fades, pressure builds, and the familiar rules of life bend into something entirely new. For most of us, the ocean is a surface thing. We think of it as waves and tides, storms and sunlit beaches, a restless blue expanse that stretches to the horizon. We picture ships skimming across it, whales breaking through it, and maybe, if we're feeling adventurous, a diver or a submarine dipping a little below. But the truth is, the ocean is not a surface. It's a vast vertical wilderness, a three-dimensional world that extends downward far beyond what our eyes or imaginations easily grasp. If you were to sail over the spot where the Milwaukee Deep yawns open in the Puerto Rico Trench, the water beneath you would stretch downward more than 27,000 feet, about 5 miles, into the Earth. To put that in perspective, if Mount Everest were placed inside the trench, its summit would still be more than a mile beneath the ocean's surface. The name Milwaukee Deep might not be familiar, even to people who know their geography well, and that's part of what makes it so intriguing. It sits quietly in the North Atlantic, just north of Puerto Rico, as part of a massive geological feature known as the Puerto Rico Trench. This trench is the deepest part of the Atlantic Ocean, formed by the slow, inexorable movement of Earth's tectonic plates. Here, the North American plate and the Caribbean plate meet and grind against each other, a colossal and ancient collision that has carved out a chasm deeper than almost anything else on the planet. Milwaukee Deep is the deepest point of that trench, a single, silent pocket of water so remote and hostile that only a handful of machines, and no humans, have ever been there. It's strange, isn't it, to think that our planet still holds places we've barely touched. We've walked on the moon, sent probes beyond the edge of the solar system, and built telescopes that peer into the beginnings of time itself, and yet, here on Earth, under the same oceans that cover more than 70% of our planet's surface, lie regions that remain almost entirely unexplored. The Milwaukee Deep is one of those places. It is part of what scientists call the hadal zone, a term derived from Hades, the Greek underworld, reserved for ocean depths below 6,000 meters. It is a realm of crushing pressure, total darkness, near freezing temperatures, and life forms so bizarre they might as well be science fiction. But it's also a place that holds answers about Earth's past, about how life adapts to extremes, and maybe even about how life began in the first place. Before we plunge toward the bottom, it's worth pausing to understand what makes such a place possible. The Earth's crust is not a single, unbroken shell. It's a mosaic of massive plates, slowly shifting and colliding atop a deeper molten mantle. Where these plates meet, extraordinary things happen. Mountains rise, volcanoes erupt, and trenches like the Puerto Rico Trench form. In the case of Milwaukee Deep, the North American plate is slowly sliding beneath the Caribbean plate in a process known as subduction. Over millions of years, this grinding motion has gouged a deep gash into the ocean floor. Unlike the dramatic volcanic arcs of the Pacific's Ring of Fire, the Puerto Rico Trench is a quieter scar, cold and still. Its depth, a record of tectonic patience measured in inches per year. It's hard to grasp what depth really means in the ocean. 5 meters underwater feels deep if you're holding your breath. 50 meters is deeper than most recreational divers will ever go. The Titanic lies about 3,800 meters below the surface. Milwaukee Deep is more than twice that. At its bottom, the pressure is over 8,000 pounds per square inch, more than 1,000 times what we experience at sea level. Every square inch of any object down there must withstand the weight of a small car pressing against it. A human without protection would be crushed instantly. Even most submarines would implode long before reaching that depth. Only the most carefully engineered robotic vehicles, encased in titanium and glass spheres, have ever dared to visit. The first to measure and name the Milwaukee Deep were sailors aboard the USS Milwaukee, a US Navy cruiser conducting depth soundings in 1939. At the time, deep-sea exploration was still in its infancy, relying on weighted lines and rudimentary sonar. The cruise measurements revealed a startling depth of over 8,300 meters, a figure later refined by modern equipment but remarkable for its time. The name Milwaukee Deep stuck, a quiet nod to the ship that first glimpsed this hidden chasm. In the decades since, scientists have returned with more sophisticated tools, using multi-beam sonar and autonomous underwater vehicles to map the trench with increasing precision. Yet for all that technology, the deep remains mostly unknown. Less than 5% of the world's ocean floor has been mapped in high detail, and the hadal zones, including Milwaukee Deep, are among the least understood environments on Earth. Imagine yourself descending into that world. The surface above is bright and busy, home to ships, storms and sunlight. But as you sink, the light quickly fades. By 200 meters, you're in the twilight zone, where sunlight weakens and colours shift to blue. At 1,000 meters, the last hint of daylight disappears entirely. Beyond this point lies the midnight zone, a realm of perpetual darkness. Down here, the pressure grows relentless, the temperature drops close to freezing, and life becomes stranger with every passing meter. Still, deeper you go, past 4,000, 6,000, 8,000 meters. The water becomes a crushing weight, the silence absolute. Somewhere below, at the trench floor, the Milwaukee Deep waits, silent, cold, and ancient. It's tempting to imagine the deep ocean as lifeless, but nothing could be further from the truth. Even in the hadal zone, where conditions are extreme beyond imagination, life persists. Not the kind of life we know from coral reefs or coastal shallows, but life adapted to darkness, pressure, and scarcity. These organisms are not just survivors, they are specialists, shaped by millions of years of evolution to thrive where few others can. Some are tiny amphipods, shrimp-like creatures with flexible exoskeletons that withstand the crushing pressure. Others are translucent snailfish, their gelatinous bodies free from the gas-filled swim bladders that would collapse at these depths. There are microbes too, vast communities of them, living on and within the sediments, feeding on chemical energy rather than sunlight, quietly driving the cycles of life in this dark world. Even the water itself tells a story. In the hadal depths, the ocean is layered and still, separated from the churning surface above. Here, cold, dense water formed near the poles slowly creeps along the seafloor, taking centuries or even millennia to make its way around the globe. With it come particles of organic matter, the remains of plankton, bits of plants, fragments of animals, drifting downward like marine snow. Most of it is consumed long before it reaches the bottom. but a fraction survives, settling into the sediments that carpet the trench floor. These sediments are not just mud, they are archives. Layer by layer, they record the history of the ocean and the planet, volcanic eruptions, climate shifts, even traces of human activity. Scientists who recover cores from the trench floor can read these layers like pages in a book, each one a snapshot of a moment in Earth's deep past. And there are human fingerprints here too, faint but unmistakable. Microplastics, industrial pollutants, and traces of radioactive isotopes from nuclear tests have all been found in the deepest parts of the ocean. Even in a place as remote as Milwaukee Deep, the influence of our species has arrived. It's a sobering reminder that no corner of the planet is truly untouched, and that the choices made on the surface eventually find their way into the abyss. Yet it's also a testament to the deep ocean's role as a kind of final sink, a place where the planet's excesses settle and transform over time. Exploring a place like Milwaukee Deep is no small feat. The technology required to reach such depths pushes the limits of engineering and imagination. Remotely operated vehicles, ROVs, and autonomous underwater vehicles, AUVs, must endure pressures that would crush steel, navigate in complete darkness, and operate for hours or days far beyond human reach. Cameras and sensors must function flawlessly under immense stress. Communication with the surface is slow and limited. Even simple tasks, taking a sediment sample, collecting a water column profile, observing an organism, become complex challenges. Yet with each expedition we learn a little more. We map the contours of the trench with finer detail. We discover new species. We gather clues about Earth's tectonic behaviour, ocean chemistry, and even the possibilities for life beyond our planet. Because that's another reason why places like Milwaukee Deep matter. They're not just curiosities, they're analogues. If life can exist here, in total darkness, under immense pressure, in near freezing temperatures far from any sunlight, then perhaps it can exist elsewhere too. Maybe beneath the icy crust of Europa, one of Jupiter's moons, where a hidden ocean lies deep below. Maybe in the methane seas of Titan. Maybe in places we haven't even imagined yet. The adaptations that allow life to thrive in Milwaukee Deep. Pressure-resistant enzymes, unique metabolic pathways, symbiotic relationships with chemosynthetic microbes, offer hints about how life might adapt in alien oceans. The deep also speaks to Earth's resilience. This is a planet that constantly reshapes itself, from mountain peaks to ocean trenches. The Milwaukee Deep is a scar carved over millions of years, but it is also a living system, one that cycles nutrients, hosts life, and responds to changes above. It is a reminder that the ocean is not a passive backdrop but an active player in Earth's story, shaping climate, geology and biology in ways we are only beginning to understand. And it is a humbling reminder too that, even with all our technology and ambition, there are still places we barely know. Places that remind us of how vast, how intricate and how mysterious our own planet truly is. So here we are, poised on the edge of that darkness. Above us the surface world carries on. Ships cross the waves, storms brew and break, sunlight glints off the sea. Below us the water grows colder, the pressure heavier, the light fainter. And far beneath, beyond the reach of all but our most determined machines, the Milwaukee Deep waits in silent patience. It has been there for millions of years, watching continents drift, climates change, species rise and vanish. It will be there long after we're gone. And yet tonight, as we turn our attention toward it, it becomes more than just a point on a map. It becomes a reminder of how much there is still to learn, how much mystery still surrounds us, and how even the darkest places can hold stories worth telling. We've only just begun to sink into this abyss, and already the world above feels distant. As we descend further into the unknown, through layers of water that have never felt the warmth of the sun, the ocean begins to reveal itself in ways few ever see. The deeper we go, the stranger and more fascinating it becomes, and somewhere ahead, in that vast and silent darkness, lie the secrets of the Milwaukee Deep, a place where the planet's history, its present, and perhaps even its future are written in water and stone. If the surface of the ocean is a familiar world of wind and waves, sunlight and storms, then the depths beneath are another planet entirely, one layered and complex, each level stranger and more challenging than the one above. To understand the Milwaukee Deep and what it means to reach the very bottom of the Atlantic, we first have to travel through everything that lies above it. Because the deep isn't a single place you drop into like a cave. It's a gradient, a slow and relentless transformation of the sea as you descend from light into darkness, from warmth into cold, from the world we know into one that feels utterly alien. The ocean doesn't end where the surface disappears from view. It changes quietly and profoundly until you arrive somewhere that hardly seems part of Earth at all. If you were to begin at the surface and slowly make your way down, you'd pass through a series of invisible thresholds, each one marking a shift in the environment and the life that can exist there. The first is the epipelagic zone, often called the sunlight zone, and it extends from the surface down to about 200 meters. This is the ocean most of us know, the world of shimmering blue water, drifting plankton, darting fish, and the vast migrations of whales. Sunlight penetrates deeply enough here to support photosynthesis, fueling the entire marine food web. Everything from tiny phytoplankton to massive predators thrives in this bright and dynamic layer. It is busy, noisy, and alive, pulsing with energy from the sun. But beyond that point, the light begins to fade. The next layer, stretching from about 200 to 1,000 meters, is known as the mesopelagic zone, the twilight zone. Here, sunlight dwindles to a dim, ghostly glow, too weak to sustain photosynthesis. Colours shift as red light disappears first, leaving only shades of blue and green. It is a place of transition, where surface creatures venture downward and deep sea species rise at night to feed. This daily movement, known as the Deal vertical migration, is the largest animal migration on the planet, happening every day, unnoticed by most of us. Billions of fish, squid, and zooplankton travel hundreds of meters up and down in a ceaseless rhythm, following the light and the safety it brings. As you descend deeper still past 1,000 meters, you enter the bathypelagic zone, the midnight zone. Here, sunlight vanishes completely. The darkness is total and permanent. The pressure is immense, hundreds of times what we feel at sea level. Temperatures hover just above freezing. This region extends down to about 4,000 meters and is home to creatures that seem born from another world. Anglerfish with glowing lures, gulper eels with gaping jaws, and translucent jellyfish that pulse gently through the black. Many of them produce their own light through bioluminescence, creating a galaxy of flickering signals in the darkness, flashes to lure prey, attract mates, or confuse predators. It's a language of light in a world without sun. Beneath that lies the abyssopelagic zone, the abyssal plain, stretching from about 4,000 to 6,000 meters. The name is fitting. This is the largest habitat on Earth, covering more than half of the planet's surface, and yet it is almost entirely unexplored. Here, the seafloor flattens out into vast plains of fine sediment, broken occasionally by seamounts and ridges. The water is near freezing, the pressure staggering, and life moves slowly, shaped by scarcity and patience. Gigantic sea cucumbers creep across the mud. Deep-sea starfish and brittle stars drift in the gentle current. Strange fish with slow metabolisms and delicate bodies wait for food to fall from above. There is no rush here, no seasons or storms, only the steady rain of marine snow, the remains of life from the surface, drifting down like ash from a distant fire. And then finally you reach the hadal zone, the deepest, most extreme region of the ocean, beginning around 6,000 meters and plunging down into the planet's most profound trenches. This is the realm of Milwaukee Deep. It is a world defined by extremes, pressure more than 1,000 times greater than at the surface, temperatures barely above freezing, total darkness, and isolation beyond anything we experience on land. It is also a place of immense geological power. Trenches like the Puerto Rico Trench are born from the grinding of tectonic plates, their shapes carved over millions of years by the slow subduction of one plate beneath another. The result is not a narrow crack, but a vast scar, a V-shaped valley stretching hundreds of kilometers long and dozens wide, descending into a darkness that swallows light, heat, and almost everything else. The Milwaukee Deep sits within this trench like a hidden chamber, a pocket within a pocket deeper than the rest. Its maximum depth is measured at about 8,376 meters, not as deep as the Mariana Trench's Challenger, deep in the Pacific, but still staggering. It is the lowest point in the Atlantic Ocean, the deepest any part of this vast ocean basin descends. And because the Atlantic is bordered by continents rich in history and human presence, the Milwaukee Deep holds a particular fascination. It is a reminder that even in an ocean that carried explorers, empires, and entire civilizations, there remain places so remote and hostile that they might as well exist on another planet. To reach a place like this is not simply a matter of going down. Each meter deeper is another layer of difficulty. Pressure increases by about 1 atmosphere, roughly the pressure of the air at sea level, for every 10 meters you descend. By 1,000 meters, the pressure is 100 times what we feel on land. By the time you reach the bottom of Milwaukee Deep, it's more than 800 times greater. Steel hulls buckle, air-filled spaces collapse. Even the chemistry of water changes under such force, becoming denser and more viscous. Life must adapt or perish. That it exists here at all is one of nature's most astonishing feats. But adaptation is everywhere in the deep. The creatures that live in the hadal zone have evolved to survive conditions that would destroy most life. Their cell membranes are reinforced to remain flexible under pressure. Their proteins and enzymes are shaped to function in near-freezing water. Many have no gas-filled cavities that could be crushed. Some species use pressure itself as part of their biology, relying on it to stabilize their cellular structures. And because food is scarce, many have evolved slow metabolisms, conserving energy and surviving on the faint trickle of organic matter that drifts down from the surface. Some even rely on chemosynthesis, harnessing energy from chemical reactions rather than sunlight, a process more often associated with hydrothermal vents, but also present in the sediments of deep trenches. The hadal zone is also shaped by geology in ways the rest of the ocean is not. The Puerto Rico Trench, for example, is a product of immense forces at work over millions of years. As the North American plate slides beneath the Caribbean plate, it drags the seafloor downward, creating a deep, curving trough. This movement is not smooth or steady. It is punctuated by earthquakes and occasional tsunamis, reminders that the trench is not just a passive feature, but an active boundary in the planet's crust. These tectonic shifts influence everything from the shape of the trench walls to the distribution of sediments at the bottom. Over time, layers of fine particles settle, burying traces of volcanic eruptions, storms, and even human activity. They accumulate so slowly, sometimes just a few millimeters per 1,000 years, that each centimeter of sediment can represent vast spans of time, a geological archive hidden in darkness. Studying such places is incredibly difficult. The very conditions that make the Milwaukee Deep so fascinating also make it nearly inaccessible. Human-occupied submersibles, like those that visited the Mariana Trench, are rare and expensive. Most exploration here is done with unmanned vehicles, remotely operated vehicles, ROVs, or autonomous underwater vehicles, AUVs, that can survive the crushing pressure and transmit data back to the surface. Even then, missions are complex and risky. Communication signals weaken over such depths. Navigation is imprecise without GPS, which cannot penetrate water. Instruments must be built to function reliably in near-freezing temperatures and under immense stress. A single expedition can take years to plan and execute, and the smallest failure, a leak, a malfunctioning thruster, a software glitch, can mean the loss of a machine worth millions. Despite these challenges, our understanding of the Milwaukee Deep and other hadal zones has grown dramatically in recent decades. Advances in sonar mapping have revealed the trench's contours in remarkable detail, showing steep walls, slumping sediment slopes, and occasional fault lines. Pressure-resistant landers, robotic platforms that sink to the seafloor and return to the surface after completing their missions, have captured high-resolution images and collected samples of water, sediment and organisms. These samples have revealed new species, unexpected chemical processes, and even traces of pollutants carried from thousands of kilometers away. Each discovery is a reminder that even in the planet's most remote corners, the reach of the surface world is felt. One of the most striking revelations from these explorations is just how connected the deep ocean is to the world above. The Milwaukee Deep is not isolated from the rest of the planet. It is shaped by what happens at the surface, by climate patterns, ocean currents, and even human activity. Organic matter that begins as a bloom of plankton near the surface can, over weeks or months, sink slowly to the trench floor, feeding the organisms that live there. Microplastics shed from synthetic fabrics and packaging can travel across oceans and settle into hadal sediments. Even radioactive isotopes from nuclear tests conducted decades ago have been detected in deep-sea trenches. The abyss may seem remote, but it is part of a planetary system that connects every drop of water, every current, every breath of wind. This connection is not just ecological, but also geological. The subduction zone that created the Puerto Rico Trench is part of the vast engine that drives plate tectonics, the same engine that shapes continents, builds mountains, and fuels volcanic eruptions. As the North American plate sinks beneath the Caribbean plate, it carries water and sediments deep into the Earth's mantle. There, under immense heat and pressure, they can trigger volcanic activity or alter the composition of the mantle itself. The trench, in other words, is not just a passive feature of the seafloor. It is part of the planet's circulatory system, recycling crustal material and driving the long-term evolution of Earth's surface. This is one of the reasons scientists are so eager to study trenches like Milwaukee Deep. They are windows into the deep processes that shape our world. They offer clues about how continents move, how earthquakes form, and how the deep earth and the surface interact. They also hold records of the past, layers of sediment that capture changes in climate, ocean chemistry, and even biological evolution over millions of years. By studying these layers, scientists can reconstruct how the planet's environment has shifted over time, offering insight into how it might change in the future. In a world grappling with rapid climate change, such long-term perspectives are invaluable. Yet, for all we've learned, what we don't know is still far greater. Vast stretches of the trench remain unmapped. Entire ecosystems may exist that we have never seen. Chemical processes we don't yet understand may be unfolding in the darkness. New species with adaptations we can barely imagine may be thriving under pressures that would crush steel. The deep ocean is, in many ways, Earth's final frontier, not because it is unreachable, but because it resists easy exploration. It demands patience, ingenuity, and humility. It reminds us that discovery is not a matter of conquest, but of careful, deliberate effort. And there's something profoundly humbling about that. We live in an age of extraordinary technological power. We've split the atom, mapped the human genome, and sent spacecraft beyond the edge of our solar system. And yet, beneath our own oceans, in a world that covers most of our planet, we are still beginners. The Milwaukee Deep, the deepest point in the Atlantic, is a reminder of that humility. It's a reminder that Earth is not fully known, that mystery is not something confined to distant galaxies or theoretical physics. It's right here beneath the waves, waiting in silence. As we continue our slow descent through this layered world, the ocean begins to feel less like a familiar place and more like a vast living system, one that connects surface and seafloor, sunlight and darkness, the present and the deep past. Each layer we pass through is part of that system, each change in light, pressure and life, another chapter in the ocean story. And somewhere far below, where the weight of the sea crushes everything into silence and darkness, that story reaches one of its most profound and mysterious points. The Milwaukee Deep is not just a location on a map. It is the end of the ocean as we know it, and the beginning of something else. A realm where the rules change, where life is redefined, and where the planet reveals a part of itself that most of us will never see. The deeper we go, the more the ocean transforms from a place into an experience, one that defies our senses and challenges our assumptions. And yet, even in this alien darkness, there is continuity. The same water that laps against our shores flows here. The same forces that shape our continents carve these trenches. The same life that thrives in coral reefs leaves traces that drift down to feed organisms in the hadal zone. The ocean does not end. It simply becomes something different, something stranger, something more. And as we approach that difference, as we peer into the heart of the Milwaukee Deep, we begin to glimpse not just the structure of the planet, but its soul. Ancient, vast, and still holding secrets in the dark. The ocean changes profoundly with depth, but nothing marks that transformation more completely than the moment light disappears. Above, the sea is a shifting, glittering mirror, alive with colour and motion. Sunlight spears through the surface, scattering into rippling beams that dance over shoals and coral and the silver bodies of schooling fish. Even as you descend into the twilight zone, there's still a sense of connection to the world above. A dim blue glow that speaks of the surface just out of reach. But then, slowly, inevitably, that connection fades. By 1,000 meters, the light is gone. There is no dawn, no dusk, no day. There is only darkness, endless, unbroken, and absolute. This is not the darkness of a moonless night or a deep cave. It's deeper than that, older, heavier. It is the default state of most of the planet, a feature, not a flaw. More than 90% of the ocean's volume exists in permanent darkness. The sunlight that shapes life on land and in shallow seas never reaches here. Even the strongest beams are scattered and absorbed long before they can penetrate this far. The deep ocean exists in a perpetual midnight, a world without seasons or shadows, where the rhythms of day and night are meaningless. In this place, the sun might as well not exist. For humans, it's difficult to imagine such a world. We are creatures of light, evolved in a world defined by its presence and absence. Our eyes, our sleep cycles, even our emotions are tied to the rising and setting of the sun. We build our lives around it, measuring days, months, and years by its path across the sky. Yet, for the vast majority of Earth's biosphere, light is irrelevant. Life here evolved not in response to sunlight, but in its absence, adapting to a world where vision is useless, colour meaningless, and time marked by forces other than the turning of the Earth. In this world without light, pressure is the first and most unforgiving fact of existence. Every 10 metres of depth adds another atmosphere of pressure, about 14.7 pounds per square inch. At 8,000 metres, the pressure is more than 800 times greater than at the surface. To put that in perspective, it's like having 50 jumbo jets stacked on top of you. Any structure not designed to withstand it would be crushed instantly. Air-filled cavities collapse, metal bends, human lungs would implode long before reaching these depths, and yet life persists, not in spite of the pressure, but because of it. The organisms that call this place home are shaped by it, their very biology built around the immense force that surrounds them. One of the most striking adaptations is the absence of rigid gas-filled structures. Many deep-sea creatures lack swim bladders, the buoyancy organs that help fish regulate their depth, because the gas inside them would compress under pressure, making them useless or even lethal. Instead, these animals rely on soft, gelatinous bodies that resist compression, or they match the density of the surrounding water to achieve neutral buoyancy. Their tissues often contain high concentrations of special molecules known as piezolites, which stabilize proteins and membranes under intense pressure. Without these adaptations, the fundamental chemistry of life would fail. Vision too takes on new forms in the dark. Eyes become enormous to capture even the faintest glimmer of light, or they disappear altogether, replaced by heightened senses of touch, vibration, and chemical detection. Some species develop photophores, specialized organs that produce light through chemical reactions. Bioluminescence is one of the defining features of the deep ocean, a language of flashes and glows used for communication, hunting, and camouflage. It's estimated that up to 90% of deep-sea organisms produce their own light in some form. In the absence of sunlight, evolution has written its own version of illumination. Consider the anglerfish, a predator perfectly adapted to this darkness. It drifts motionless in the black, its body nearly invisible, while a long filament extends from its head, tipped with a glowing lure. The light attracts prey in a world where brightness is rare and often means food. When an unsuspecting fish approaches, the anglerfish strikes, swallowing it whole with jaws that can open wider than its own body. It's an elegant adaptation to a world where energy is scarce and opportunities fleeting. Other creatures use light for deception. Some squids emit bursts of bioluminescence to startle predators and escape. Certain shrimp eject glowing clouds as decoys. Even bacteria participate, forming symbiotic relationships with hosts to provide light in exchange for nutrients. But light is not the only form of communication here. In the absence of visual cues, many deep-sea animals rely on chemical signals, complex cocktails of molecules that carry messages about territory, reproduction, and danger. Others are exquisitely sensitive to vibration, detecting the faintest disturbances in the water caused by swimming prey or approaching predators. Some species, like the giant grenadier, have lateral line systems, rows of sensory cells that detect pressure changes, allowing them to feel their surroundings in 3 dimensions. In the deep, survival depends on sensing a world that is invisible. It's not just the animals that adapt. The entire ecosystem is shaped by the absence of light. On land and in the sunlit ocean, life is built on photosynthesis, the process by which plants and algae use sunlight to convert carbon dioxide and water into energy. In the deep sea, that is impossible. Instead, life depends on the rain of organic matter from above. Tiny particles of dead plankton, fecal pellets, and other detritus collectively known as marine snow. It falls constantly, though slowly, taking weeks or months to reach the seafloor. Most of it is consumed along the way, stripped of nutrients by scavengers and decomposers. By the time it reaches the depths of Milwaukee Deep, only a fraction remains. That scarcity shapes everything. Food is precious and energy is conserved. Many deep-sea creatures grow slowly, reproduce infrequently, and live long lives. Some fish mature over decades and may live for more than a century. Others survive on meals spaced weeks or months apart. Predators rely on patience and stealth, waiting for opportunities rather than chasing them. Scavengers roam the seafloor guided by faint chemical trails, searching for the rare carcass of a whale or shark that has sunk from the surface. Events known as whale falls that can sustain entire ecosystems for decades. In the deep, nothing is wasted. Every scrap of energy is recycled, every opportunity seized. Yet even here, in a world seemingly cut off from the sun, there are exceptions to the rule of marine snow. Some life forms draw energy not from the surface but from the earth itself. Chemosynthetic bacteria use chemical reactions, often involving methane, hydrogen sulfide or other compounds seeping from the seafloor to produce energy. These microbes form the base of unique ecosystems that exist entirely independently of sunlight. In some trenches, microbial mats carpet the sediment, feeding small invertebrates, which in turn support larger predators. These systems are thought to resemble the earliest ecosystems on Earth, and they offer tantalizing clues about how life might exist elsewhere in the universe, in places far from any star. The geology of the deep also plays a role in shaping this lightless world. The Puerto Rico Trench, home to Milwaukee Deep, is not a flat, featureless plain. Its walls rise steeply, scarred by landslides and fault lines. Cold seeps, places where fluids rich in methane and other chemicals escape from the seafloor, dot the landscape, creating oases of life in the darkness. Earthquakes occasionally shake the trench, sending clouds of sediment billowing into the water and triggering underwater avalanches that reshape the terrain. Even the slow drift of tectonic plates leaves its mark, altering the shape of the trench over millions of years. This is a dynamic world, not a static one. A place where change happens slowly but relentlessly. The silence here is profound. Sound behaves differently under pressure, travelling farther and faster through the dense water. Many deep-sea creatures rely on low-frequency sounds to communicate, sounds that can carry for kilometres through the dark. Scientists studying these depths have detected mysterious noises, long, low moans and sharp, percussive clicks, whose sources remain unknown. Some are likely geological, the groaning of shifting plates or the rumble of distant earthquakes. Others may be biological, the calls of species we have never encountered. The deep ocean remains one of the least understood acoustic environments on Earth, a vast, dark concert hall filled with sounds we have yet to decipher. It's tempting to think of this world as alien, but in many ways it is deeply connected to our own. The water that fills Milwaukee Deep is part of the global ocean circulation, a slow, planet-spanning conveyor belt driven by differences in temperature and salinity. Cold, dense water sinks in the polar regions and creeps along the seafloor, eventually rising again in distant parts of the world. This circulation helps regulate Earth's climate, storing and transporting heat around the globe. The deep ocean also absorbs vast amounts of carbon dioxide from the atmosphere, playing a crucial role in buffering the planet against climate change. What happens in the darkness of the Milwaukee Deep is not isolated from the world above. It is part of the planet's beating heart. Humanity's relationship with this darkness is still in its infancy. For most of history, the deep ocean was a place of myth and imagination, a realm of sea monsters and bottomless pits. It wasn't until the 19th and 20th centuries that we began to probe its depths with any real success. Even today, our glimpses into the hadal zone are fleeting and fragmentary. The challenges are immense: crushing pressure, extreme cold, and the sheer logistical difficulty of reaching such remote places. Yet each expedition reveals something new, a species never before seen, a chemical process we didn't know existed, a geological feature that reshapes our understanding of Earth's dynamics. Those discoveries also reveal our impact. Even here, in the most remote depths, traces of humanity are present. Microplastics, invisible to the naked eye, have been found in hadal sediments. Pollutants like PCBs and heavy metals carried by ocean currents accumulate in the tissues of deep-sea organisms. Even carbon from fossil fuel emissions dissolved into the ocean eventually reaches these depths, altering the chemistry of the water and the sediments. The deep is not untouched. It is part of the same interconnected system that links rivers and rain, forests and cities, surface and abyss. This raises important questions about our future relationship with the deep ocean. As technology advances, industries are eyeing the seabed as a source of valuable minerals, cobalt, nickel, rare earth elements, essential for batteries and electronics. Some of these resources lie in deep-sea sediments or on the slopes of trenches like the Puerto Rico Trench. Extracting them would be technically challenging and environmentally risky. Disturbing sediments could release stored carbon or disrupt fragile ecosystems. Noise and light from mining operations could affect species that have evolved in silence and darkness for millions of years. The consequences are difficult to predict because we understand so little about how these ecosystems function. For now, Milwaukee Deep remains largely undisturbed, a place of study rather than exploitation. But as pressure grows to secure resources, the deep ocean may become a new frontier, and with it will come difficult choices about how much we are willing to risk for what we gain. Protecting places like this is not just about preserving biodiversity, it's about safeguarding a part of Earth's life support system, one that we depend on in ways we barely understand. It's about recognizing that even the darkest corners of our planet are connected to our lives in ways that matter profoundly. And perhaps that's the most remarkable thing about this world without light. It is not empty, it is not lifeless, it is not irrelevant. It is a vital part of Earth's story, ancient, dynamic, and deeply connected to everything else. It challenges our assumptions about what life needs and where it can exist. It reveals the power of adaptation, the resilience of ecosystems, and the complexity of the planet we call home. It reminds us that the boundaries we imagine, between light and dark, surface and depth, life and void, are often less absolute than they seem. As we drift deeper into this darkness, the ocean becomes less a place and more a presence, vast, silent, indifferent, and yet essential. It holds the weight of history, the memory of geological forces, the traces of life that lived and died above. It is a place where time moves differently, where change is measured not in days or seasons, but in millennia. And somewhere, far below, in the stillness of Milwaukee Deep, the story of the ocean, and perhaps of life itself, continues to unfold, unseen and uninterrupted. This darkness is not an end. It is a beginning. It is the backdrop against which everything else takes shape. The foundation of the ocean's structure, the cradle of its strangest forms of life, the stage upon which some of Earth's most profound processes play out. And as we continue our descent into this realm without light, we move closer to understanding not just the deep ocean, but the planet itself, its history, its dynamics, and its astonishing capacity for life in even the most unlikely places. There's something uniquely human about our urge to go deeper. We climb mountains because they're there. We send spacecraft into the void because the horizon isn't enough. And when it comes to the ocean, we are drawn to its depths with a mix of fear and fascination. Standing on a ship above the Puerto Rico Trench, it's impossible to imagine what lies beneath. The surface looks the same as anywhere else, a rolling expanse of water, maybe a few seabirds, the wind carrying salt across the deck. But below, more than 8 kilometers down, is a world we barely understand. To get there is not just a matter of depth, it's a journey through pressure, darkness, and time itself. It is, in the truest sense of the word, a descent, not just downward, but inward, into the hidden structure of our planet. The descent into a place like Milwaukee Deep begins long before anything enters the water. It starts with planning, because reaching the deepest parts of the ocean is one of the hardest things humanity has ever attempted. Every detail matters. Pressure at the bottom exceeds 8,000 times that at the surface, so any vessel or probe must be engineered to withstand forces that would crush a submarine like a tin can. Communication systems must operate in a medium that swallows radio waves and distorts sound. Navigation must be done without GPS, which cannot penetrate water. Every component, or from the smallest sensor to the thickest hull, that must be tested, retested, and tested again, because failure at 8,000 meters is not an inconvenience. It's the end of the mission. For most of history, such a descent was impossible. Humans could dive a few dozen meters with weighted stones, and later, with early diving suits, they pushed to perhaps 100 meters. The first real breakthrough came in the 20th century with the invention of bathyscarfs, freediving submersibles designed to carry humans into the deep. In 1960, Jacques Piccard and Don Walsh descended to the bottom of the Mariana Trench aboard the bathyscarf Trieste, reaching a depth of 8,911 metres. Their journey lasted nearly 5 hours down and 3 hours up, all spent in a tiny steel sphere with walls thicker than a bank vault. The Trieste was a crude machine by modern standards, but it proved that the deepest parts of the ocean were within reach. Since then, only a handful of crewed missions have ventured into the hadal zone, and most exploration is now done by unmanned vehicles. If you were to ride one of these vessels into the Milwaukee Deep, your journey would begin at the surface in calm blue water. The light would scatter in shifting patterns around you, fish darting just below, the hull rocking gently with the waves. Then the descent would begin. Motors would hum softly, ballast tanks releasing air, and the vessel would start to sink. Slowly at first, then faster, as gravity and buoyancy reached a balance. The water outside would grow darker and colder with every passing metre. The surface would fade from view within minutes, replaced by a vast blue emptiness. At 100 metres, the pressure is already 10 times greater than at sea level. Sunlight still filters down, but the colours begin to change. Reds and oranges disappear first, absorbed by the water. Yellows and greens fade next. By 200 metres, only blue remains, a pale ghost of the light above. Fish become rarer, and the first signs of the twilight zone appear, small, silvery creatures with large eyes, adapted to the dimness. Tiny plankton drift in slow spirals, and translucent jellyfish pulse gently in the gloom. The water feels heavier now, the weight of the ocean pressing in from all sides. By 500 metres, you're well into the mesopelagic. Sunlight is a distant memory, and the darkness grows with each passing moment. Creatures here have evolved to survive on the edge of visibility. Many migrate vertically each day, rising to feed at night and sinking again before dawn. Some have light-sensitive organs tuned to the faintest glimmer from above. Others produce their own light, flashing and glowing in patterns that serve as lures, warnings, or signals. Schools of lanternfish drift past, their bodies studded with points of green and blue. A siphonophore, a colonial organism longer than a whale, floats in the distance, its bioluminescent tendrils trailing like a living chandelier. At 1,000 metres, you cross the boundary into the midnight zone. The last traces of sunlight are gone. The darkness is total. Outside, the temperature hovers just above freezing, and the pressure is crushing. It's an alien world now, and everything you see reflects that. The fish are fewer but stranger, elongated bodies, oversized jaws and needle-like teeth. Many are soft and gelatinous, lacking bones that would shatter under pressure. They drift rather than swim, conserving energy in a place where food is scarce. The silence is profound, broken only by the occasional creak of the hull as it adjusts to the increasing pressure. At 2,000 metres, the descent becomes more psychological than physical. The scale of the ocean starts to overwhelm the senses. You're surrounded by water in every direction, not just above and below, but stretching thousands of kilometres horizontally as well. The nearest surface is farther away than the top of Mount Everest is from sea level. It's difficult not to feel small here, suspended in the vastness, moving slowly toward a place that has existed unchanged for millions of years. Even the machines built to explore this realm often move at little more than a metre per second. The journey is measured not in minutes, but in hours. At 4,000 metres you enter the abyss. The water is denser here, its weight pressing relentlessly against every surface. The creatures are even more specialised. Some are blind, relying entirely on vibration and chemical cues. Others have evolved transparent bodies to remain invisible in the darkness. The seafloor is still far below, but now and then you might see signs of its presence. A drifting clump of sediment, a fragment of organic matter slowly sinking, perhaps the faint shadow of a seamount rising from the depths. Communication with the surface grows weaker, the delay between signals more noticeable. You are far from the world above now, in every sense. The final stage of the descent, from 6,000 meters down to the bottom, is the most demanding. The pressure is now hundreds of times greater than at the surface, and every additional meter adds another layer of stress to the vessel. The environment outside is nearly uniform, pitch black, near freezing, utterly silent, but subtle changes reveal themselves to the trained eye. The density of the water increases slightly. The composition of the microbial life shifts. The chemical gradients near the seafloor become more pronounced, and then, slowly, the bottom begins to appear. At first, it's just a faint haze, a reflection of the submersible's lights on suspended particles. Then, as you draw closer, the seafloor emerges from the dark, a pale, undulating plain stretching into the distance. Touching down at the bottom of Milwaukee Deep is an experience few have ever had. The descent may have taken more than 4 hours, yet the stillness of the seafloor makes time feel irrelevant. The sediments here are soft and fine, a mixture of mineral particles, organic matter and microscopic shells that have drifted down over millennia. They are undisturbed, shaped only by slow currents and the occasional fall of debris from above. It is a landscape without weather, without waves, without light. A place where change happens at a glacial pace. A footprint here could last for centuries, and yet, this is not an empty world. Even here, nearly 9 kilometers below the surface, life persists. Small amphipods scuttle across the sediment, feeding on detritus. Strange, translucent snailfish hover just above the bottom, their bodies adapted to the immense pressure. Tiny worms burrow through the mud, processing organic material that has drifted down from the surface. Bacterial mats spread across patches of sea floor, harnessing chemical energy from the sediments. It is a sparse ecosystem, but a resilient one, built on efficiency and adaptation. Every organism here is a testament to life's ability to endure. The seafloor itself tells a story as well. It is not flat, but gently sloping, shaped by landslides and sediment flows from the trench walls. Occasional mounds mark places where methane seeps through the sediment, feeding chemosynthetic communities. In some areas, layers of sediment are disturbed by tectonic activity, evidence of earthquakes that ripple through the trench as the North American and Caribbean plates grind against each other. Even here, in the deepest part of the Atlantic, the Earth is not still. It shifts and breathes, reshaping the landscape over millennia. If you were to gather a sample of that sediment and analyze it, you would find a record stretching back hundreds of thousands of years. Layer upon layer, each one laid down by the slow rain of particles from above. Some layers might contain microscopic shells from plankton that lived when the climate was warmer or colder. Others might carry traces of volcanic ash from distant eruptions. Still others could hold the faint signature of human activity. Carbon from the burning of fossil fuels, radioactive isotopes from nuclear tests, microplastics from the breakdown of synthetic materials. Even here, far from human eyes, the fingerprints of our species are present. The descent into the Milwaukee Deep is not just a physical journey. It's a journey through time and scale, through the limits of what life can endure and what technology can achieve. It forces us to confront the vastness of the ocean and the complexity of the planet. It challenges our assumptions about where life can exist and how it adapts. And it reminds us that Earth is not fully known, that even now in the 21st century there are places we have barely touched. The experience also changes how we think about the ocean as a whole. It's easy to think of the sea as a surface phenomenon, waves, tides and currents. But descending into the hadal zone reveals it as something else entirely, a vast interconnected system that spans from the air above to the rocks below. The surface and the deep are not separate worlds but parts of the same whole, linked by currents, chemistry and life. The particles that drift down from the surface feed the organisms in the depths. The water that sinks here helps drive the global circulation that shapes climate. The tectonic forces that create trenches like Milwaukee Deep also build mountains and trigger earthquakes on land. The ocean is not just water, it is a process, a system, a living part of the planet. The descent also changes how we think about ourselves. Humans evolved on land in air and sunlight. Our senses, our physiology, even our psychology are tuned to that environment. The deep ocean is profoundly different. It is hostile to our bodies, alien to our senses, and indifferent to our presence. Yet, with ingenuity and persistence, we've found ways to enter it, to study it, to learn from it. Each descent into a place like Milwaukee Deep is a reminder of both our limitations and our capabilities. We are fragile creatures, yet we build machines that can withstand the weight of the ocean. We are bound to the surface, yet we reach into the abyss. We are finite beings, yet we seek to understand the infinite. It's worth noting too that every descent is temporary. No vessel can stay in the hadal zone indefinitely. Batteries drain, materials fatigue, and communication becomes increasingly unreliable. After a few hours on the seafloor, the ascent must begin. Ballast is released, and the vessel slowly rises. The darkness remains, but the pressure eases with each meter. The temperature warms slightly. Faint traces of light return. The journey upward is often faster than the descent, but it feels longer, the mind still lingering on the vastness below. And yet, even as the vessel surfaces and the bright world returns, something fundamental has changed. The ocean is no longer just a flat expanse of water. It is a vertical universe, layered and complex, filled with life and history and mystery. The descent into Milwaukee Deep reveals not just the structure of the ocean, but its depth. Not just in kilometers, but in meaning. It shows us that the ocean is not an empty void, but a living system, a record of Earth's past and a key to its future. It reminds us that our planet is still wild, still unknown, still capable of humbling us with its scale and complexity. The descent does not end with the return to the surface. It lingers in the samples brought back for study, in the data recorded by instruments, in the images captured by cameras. It lingers in the questions that arise. How does life function under such pressure? What chemical processes unfold in the sediments? How do earthquakes shape the trench over millennia? What secrets are still hidden in the darkness? Each descent answers some questions and raises many more. It deepens our understanding and sharpens our curiosity. It invites us to return, to explore further, to look closer. And so, the descent into Milwaukee Deep is not just a journey downward. It is part of a larger journey, one that stretches across disciplines and generations, from the first sailors who sounded the depths with weighted lines, to the engineers building the next generation of deep-sea robots. It is a journey that connects geology and biology, physics and chemistry, history and future. It is a journey that reminds us that even on a planet we call home, there are still frontiers left to explore. The ocean is vast, and its deepest places are more than just measurements on a chart. They are places where Earth's most powerful forces collide, where life bends the rules of biology, where time slows and memory accumulates grain by grain. The descent into Milwaukee Deep is a way of touching that reality, of coming face to face with the planet's most extreme environments. And though we surface again, we carry that experience with us, the weight of the water, the silence of the dark, the vastness of the unknown. A reminder that there is always more to discover, more to learn, more to see. The journey downward is over for now, but the story continues. The ocean still has more to reveal, more secrets hidden in its blackest depths. And as we turn our attention from the act of descent to the world that waits there, we step deeper into the mystery. Because reaching the bottom is not the end of the exploration. It's just the beginning of understanding what it means to exist in a place where sunlight never reaches, where pressure rules every living thing, and where life has carved out a niche in the most unlikely of environments. That's where we're headed next, into the hidden communities and strange forms that call the bottom of the Atlantic home, and into the questions they raise about life itself. Far above the silence of Milwaukee Deep, the surface of the Atlantic never rests. Wind stirs the water into endless motion, storms march across the horizon, rivers pour their sediment and nutrients into the sea, and life blooms and dies in chaotic abundance. From a ship looking out over that restless expanse, it's easy to believe that whatever happens at the bottom of the ocean must be cut off from this frenzy, sealed away in a world of darkness and pressure. But that's not how the ocean works. The deep is not a closed chamber. It's a vast interconnected system, and the fingerprints of the surface reach all the way to the trench floor. Even in the quietest, darkest corners of Milwaukee Deep, traces of the surface world are present, faint, scattered, transformed by the journey, but unmistakable. These are the ghosts of the surface, the echoes of distant events and vanished lives, drifting down through the water column to shape a realm they will never see. The most constant of these ghosts is marine snow. It's an unremarkable term for something extraordinary, a slow, steady rain of particles that drifts down from the surface to the sea floor. Most of it is tiny, the remains of plankton, bits of dead algae, fecal pellets, fragments of mucus, small scraps of tissue and shell. It forms when microscopic life at the surface blooms in the sunlight, feeds, dies, and begins to sink. What starts as a vibrant sunlit ecosystem ends as a gentle snowfall in the darkness below. This rain never stops. Every second of every day particles are falling, a continuous thread linking surface and abyss. Most are consumed on their way down by scavengers and decomposers in the upper layers, but a fraction survives the journey, descending over weeks or months until it settles on the trench floor. For the organisms of Milwaukee Deep, marine snow is the foundation of life. It may seem insignificant, a grain here, a fragment there, but over time it accumulates into layers of sediment that blanket the sea floor. Each flake of snow carries with it the chemical signature of the surface: carbon from photosynthesis, nitrogen from decomposition, trace elements from terrestrial dust. As it settles, it becomes part of the deep sea ecosystem, feeding microbes that in turn support larger organisms. Without this slow rain of organic matter, the hadal zone would be a biological desert. The creatures that live here, amphipods, polychaete worms, snailfish and countless others, all depend on energy that began its journey in the light. But marine snow is more than just food. It is also a record. Each particle carries a story of the conditions at the surface when it was formed. A bloom of phytoplankton triggered by spring sunlight leaves a distinct chemical signature. A dust storm blowing off the Sahara adds iron and other minerals to the mix. A volcanic eruption can deposit layers of ash that settle into the sediments thousands of kilometers away. Over thousands of years, these layers build up like the pages of a book, preserving a history of the ocean and the planet. By drilling into the sediments at the bottom of Milwaukee Deep, scientists can read that history, reconstructing past climates, tracing shifts in ocean circulation, even identifying human impacts that reach into the most remote corners of the Earth. Some of those impacts are recent and unmistakable. Microplastics, invisible to the naked eye but ubiquitous in the modern ocean, have been found in the sediments of deep-sea trenches, including the Puerto Rico Trench. These tiny fragments, shed from synthetic fabrics, packaging, and industrial waste, drift through the water column just like marine snow. They accumulate in the same layers, become part of the same sedimentary record, and enter the same food webs. Amphipods collected from hadal depths have been found with microplastics in their stomachs, proof that even organisms living nearly 9 kilometers beneath the surface are not isolated from human activity. Other pollutants like polychlorinated biphenyls, PCBs, and mercury also make their way into the deep, carried by ocean currents and biological transport. Their presence in trench sediments is a stark reminder that no part of the planet is untouched. Even the great rhythms of the surface, the seasons, the cycles of life and death, the shifting of climate, leave their mark in the deep. In temperate regions, the spring bloom of phytoplankton creates a surge of organic material that eventually sinks, delivering a pulse of energy to the abyss. In polar regions, the melting and freezing of sea ice alters the flow of nutrients, changing the composition of the marine snow. Over longer timescales, shifts in climate can change the patterns of circulation that carry water and nutrients into the deep ocean. During ice ages, for example, colder temperatures and lower sea levels altered the density and flow of deep water, changing the delivery of oxygen and carbon to the hadal zone. Those changes are still visible today in the chemical composition of trench sediments, a ghostly record of climates long vanished. Even storms, brief chaotic events at the surface, can send echoes into the deep. Powerful hurricanes churn the upper ocean, stirring up sediments and organic matter that begin their slow descent. Landslides triggered by heavy rains or earthquakes can send massive plumes of debris cascading down continental slopes and into the deep basins. These turbidity currents, as they're known, are among the most dramatic events in the deep ocean. They can travel hundreds of kilometers across the seafloor, carving channels and depositing thick layers of sediment in trenches like the Puerto Rico Trench. In the geological record, these layers stand out as sharp boundaries, sudden, chaotic deposits among the slow, steady accumulation of marine snow. Each one marks a moment when the surface intruded violently into the deep. The biological ghosts of the surface are just as pervasive. Most of the carbon that fuels deep sea life began as a living thing in the sunlight zone. Tiny phytoplankton harnessed solar energy to grow and divide. Zooplankton fed on them. Fish and larger animals consumed the zooplankton, and when those creatures died, their bodies began the long journey downward. Some sank as intact carcasses, others as fragments, and still others as dissolved organic molecules. Even whale falls, the massive bodies of whales that die and sink to the seafloor, are part of this continuum. When a whale carcass reaches the bottom, it becomes a temporary oasis in the desert, supporting a complex community of scavengers, bacteria, and specialized worms. Over decades, the carcass is stripped, dissolved, and transformed, its energy recycled into the ecosystem. The influence of the surface extends beyond organic matter. Dust blown from deserts carries iron and other trace metals into the ocean, where they become part of the nutrient cycle. Some of that dust eventually sinks into the deep, enriching sediments and influencing microbial communities. Rivers deliver nutrients and sediments from land, shaping the chemistry of the ocean far from shore. Even atmospheric gases leave their mark. Carbon dioxide absorbed at the surface eventually mixes into the deep, where it influences the acidity and carbonate chemistry of the water. Over centuries, this process helps regulate Earth's climate, locking away vast amounts of carbon in the deep ocean and its sediments. The fingerprints of humanity are perhaps the most haunting of all the surface's ghosts. In addition to microplastics and industrial pollutants, radioactive isotopes from nuclear tests conducted in the mid-20th century have been detected in trench sediments. These isotopes, which fell from the atmosphere into the ocean decades ago, have since been transported by currents and incorporated into marine snow. Their presence provides a clear timestamp in the sedimentary record, marking the dawn of the nuclear age. It also highlights the speed and scale of human impact. In less than a century, a blink in geological time, we have left a chemical signature that extends from mountaintops to the deepest parts of the sea. There are other subtler ghosts too. Vibrations from powerful earthquakes ripple through the water column and are recorded as disturbances in deep-sea sediments. Changes in atmospheric pressure from large storms can slightly alter sea level, sending faint pressure waves that propagate downward. Even the gravitational pull of the moon, which drives the tides at the surface, reaches into the deep, creating slow, rhythmic currents that shape the distribution of sediments over millennia. The deep ocean feels the pulse of the surface in ways both dramatic and delicate, responding to forces that begin thousands of kilometers away. All of this speaks to a profound truth. The deep ocean is not isolated from the rest of the planet. It is connected to it, shaped by it, and in turn shaping it. The energy that fuels life at the bottom of Milwaukee Deep began in sunlight at the surface. The sediments that blanket the trench floor contain particles from distant deserts, ashes from ancient eruptions, and molecules from the burning of fossil fuels. The water itself has travelled across oceans and centuries to reach this place. Even in the stillness of the abyss, the surface is present, not as a direct influence, but as a memory, a ghost embedded in the fabric of the deep. These ghosts do more than link the surface and the deep. They reveal the ocean as a single interconnected system. The same currents that carry warm water to polar regions also transport nutrients and oxygen to the hadal zone. The same biological processes that drive blooms at the surface sustain microbial life in the trench. The same tectonic forces that build mountains also create the deep basins where marine snow accumulates. The ocean is not a collection of separate layers but a continuum, each part influencing and being influenced by the others. The Milwaukee Deep may seem remote, but it is woven into the fabric of the planet as surely as any coastline or coral reef. Understanding these connections is crucial, not just for science, but for the future of the planet. The deep ocean plays a vital role in regulating Earth's climate by storing carbon and redistributing heat. Changes at the surface, rising temperatures, altered circulation patterns, increased carbon dioxide, can ripple through the system and affect even the deepest trenches. Likewise, disturbances to deep-sea ecosystems can have consequences that reach back to the surface. If, for example, mining or pollution disrupts microbial communities that process carbon in the sediments, it could affect the ocean's ability to sequester carbon and influence global climate. The ghosts of the surface are not just remnants of the past. They are active forces shaping the present and future of the deep. They also serve as a reminder of the ocean's resilience and its fragility. The fact that life thrives nearly 9 kilometers beneath the surface, sustained by a slow rain of organic matter, is a testament to the adaptability of nature. Yet that same dependence makes the system vulnerable. A disruption to primary production at the surface, caused by climate change, nutrient pollution, or other factors, could cascade downward, reducing the flow of energy to the deep. The consequences might not be immediately visible, but over decades or centuries they could reshape deep-sea ecosystems in profound ways. The ghosts of the surface remind us too that the deep ocean is not a static archive but a living, evolving system. The sediments record the past, but they are also being written in the present. Each particle of marine snow that falls today will become part of the geological record tomorrow. Each chemical signal from human activity will leave a trace that persists for centuries. Even the slow, subtle changes driven by climate and tectonics are captured here, layer by layer. The Milwaukee Deep is a history book still being written, its pages turning one grain of sediment at a time. For scientists, these ghosts are more than curiosities. They are tools for understanding the planet. By studying the composition of deep-sea sediments, researchers can reconstruct past climates, track the movement of water masses, and measure the extent of human impact. By analysing the isotopic signatures of carbon and nitrogen, they can trace the sources of organic matter and the pathways it follows through the ocean. By examining microfossils, they can identify shifts in plankton communities and interchanges in temperature and nutrient availability. Every layer of sediment, every particle of marine snow, every trace of a pollutant or isotope adds a piece to the puzzle. And yet, despite all this knowledge, much remains unknown. The processes that transport material from the surface to the deep are complex and not fully understood. the interactions between microbial communities in the sediments, and the chemistry of the overlying water are still being explored. The long-term effects of pollutants on hadal ecosystems are largely speculative. Even the rate at which sediments accumulate can vary dramatically over time and space, influenced by factors we are only beginning to quantify. Each new expedition to the Milwaukee Deep reveals surprises, unexpected chemical gradients, unfamiliar species, unrecognized patterns in the sediment record. The ghosts of the surface are many, and they still have secrets to share. They are also reminders of how deeply we are tied to the ocean, even if we never see it. The carbon we release into the atmosphere eventually finds its way into the deep. The dust from our deserts, the ashes from our volcanoes, the plastics from our cities all drift downward, settling into layers that will persist long after we are gone. Even the biological rhythms of the planet, the bloom and decay of plankton, the migrations of fish, the fall of a whale's carcass, are recorded here. To look at the sediments of Milwaukee Deep is to see a reflection of the entire Earth system, from atmosphere to lithosphere, from sunlight to darkness. In the end, the ghosts of the surface are not just evidence of connection, they are proof of continuity. The deep ocean is not a separate world, but part of the same living planet that we inhabit. The rain of marine snow, the fall of whale carcasses, the drift of dust, the slow seep of pollutants, all are threads in the same fabric, and as those threads weave their way downward, they transform the abyss from an isolated void into a place rich with history and meaning. Even in the deepest, darkest parts of the ocean, the surface is present, shaping, feeding, and recording. The ghosts are everywhere, and they never stop arriving. And as they settle, as they accumulate grain by grain, they build the foundation for something more. They sustain the life that thrives in the darkness. They shape the chemistry of the water and the structure of the sediments. They preserve the memory of the planet's past and hint at its future. And they remind us that the journey from sunlight to shadow is not a one-way trip, but a constant exchange. A dialogue between the surface and the deep, carried on in particles and currents, in chemistry and life, across the vast and silent reaches of the ocean. Life, it turns out, is far more adaptable than we once imagined. For centuries, humans assumed that the deep ocean was barren, too dark, too cold, and too pressurized to support anything more complex than a few drifting microbes. Even well into the 20th century, textbooks describe the abyssal and hadal zones as biological deserts, empty voids beneath the productive layers near the surface. It was an easy assumption to make. After all, sunlight, the primary driver of life on Earth, never reaches these depths. Temperatures hover just above freezing. Pressure crushes anything not built to endure it. And yet, in the stillness of Milwaukee Deep, nearly 9 kilometers below the surface of the Atlantic, life not only exists, it thrives. It is not the exuberant, colourful life of coral reefs or coastal shallows, but a quieter, slower, more deliberate version of it, one that has adapted to a world without light and learned to endure the unendurable. The first thing to understand about life here is that it is shaped by scarcity. Energy is rare, arriving mostly in the form of marine snow or the occasional fall of a large carcass from above. Every organism must make the most of what little is available. As a result, metabolic rates tend to be slow, growth is gradual, and reproduction infrequent. Some deep-sea fish take decades to reach maturity. Others may live for a century or more. Many invertebrates grow so slowly that their lifespans stretch beyond anything we see in shallower waters. Time itself feels different here, stretched and elongated by the scarcity of energy. Yet scarcity does not mean simplicity. The ecosystems of Milwaukee Deep are complex and interconnected, built on a web of interactions as intricate as any found at the surface. At the base of that web are microbes, bacteria and archaeum that live within the sediments and on the seafloor. Some feed on the organic matter delivered by marine snow, breaking it down and recycling its nutrients. Others rely on chemosynthesis, using chemical reactions involving methane, hydrogen sulfide, or other compounds seeping from the seafloor to produce energy. These chemosynthetic microbes form the foundation of ecosystems that exist entirely independent of sunlight, much as plants do in the surface world. They feed small invertebrates like nematodes and polychaete worms, which in turn become food for larger organisms. Above this microbial layer, the next tier of life is made up of scavengers. Amphipods, small, shrimp-like crustaceans, are among the most abundant animals in the hadal zone. They are well suited to this world. Their bodies are flexible enough to resist the crushing pressure, and they can tolerate a wide range of temperatures and chemical conditions. Amphipods feed on almost anything they can find, from particles of marine snow to the remains of larger animals. They are opportunists in the truest sense, thriving in an environment where meals are unpredictable and infrequent. Some species can go months without food, slowing their metabolism to a crawl until the next opportunity drifts by. Larger scavengers patrol the seafloor as well. Deep-sea holothurians, sea cucumbers, move slowly across the sediment, ingesting it and extracting organic material as they go. These creatures are vital to the ecosystem, recycling nutrients and oxygenating the sediment as they feed. Echinoderms like brittle stars and sea stars also inhabit these depths, their delicate bodies adapted to the immense pressure. Occasionally, even larger scavengers arrive. Rat-tail fish, with their elongated bodies and slow, sinuous movements, patrol the bottom in search of food. Hagfish, blind and eel-like, slip through the mud, feeding on carcasses and detritus. These animals form the backbone of a food web that, though sparse, is remarkably resilient. Some of the most remarkable inhabitants of the hadal zone are the snailfish. These soft-bodied, translucent fish are found in trenches around the world, including the Puerto Rico Trench. They are among the deepest living vertebrates known, with some species recorded at depths exceeding 8,000 meters. Snailfish lack the gas-filled swim bladders that most fish use for buoyancy, which would collapse under the pressure. Instead, they rely on their gelatinous bodies to match the density of the surrounding water. Their bones are reduced or absent, replaced by cartilage that remains flexible even under immense pressure. Their enzymes and proteins are specially adapted to function in the cold and under crushing force. Snailfish feed on small crustaceans and other invertebrates, often hunting near the seafloor where their prey is most abundant. Adaptation is the defining feature of life in Milwaukee Deep. Every organism here is a study in evolutionary ingenuity, shaped by millions of years of selection to survive conditions that would destroy most life. Cell membranes incorporate unique lipids that remain fluid under pressure. Enzymes are structured to resist denaturation in the cold. Metabolic pathways are fine-tuned to extract the maximum possible energy from scarce food sources. Some organisms have even adapted their reproductive strategies to the constraints of the deep, producing fewer but larger eggs that develop slowly, increasing the chances of survival in an environment where juvenile mortality would otherwise be high. The absence of light has driven some of the most striking adaptations. Many species have lost their eyes entirely, relying instead on senses better suited to the darkness. Chemoreception, the ability to detect chemical signals in the water, is highly developed, allowing animals to locate food, mates, or predators by scent alone. Others are exquisitely sensitive to vibration, detecting the faint movements of prey or the approach of a predator. Some species have evolved bioluminescence, producing their own light through chemical reactions. This light is not used to see, but to communicate, lure prey, or confuse predators. In the deep ocean, light becomes a tool, a language, and a weapon. The scarcity of food means that competition is fierce, but it has also led to remarkable examples of cooperation. Symbiotic relationships are common, particularly between microbes and larger organisms. Some amphipods host communities of bacteria on their exoskeletons, which help them process nutrients or detoxify harmful compounds. Certain worms rely on internal symbionts to convert chemical energy into usable nutrients. Even in this harsh environment, life finds ways to collaborate, building partnerships that increase the chances of survival. The physical structure of the trench itself influences life in subtle ways. The steep walls of the Puerto Rico Trench create a range of microhabitats, from soft sediment plains to rocky outcrops and cold seeps. Each of these environments hosts a different community of organisms adapted to its particular conditions. The soft sediments are home to burrowing worms and bacteria that thrive on the organic matter accumulating there. Rocky outcrops provide surfaces for sessile organisms to attach and filter feed. Cold seeps, where chemical-rich fluids emerge from the seafloor, support unique chemosynthetic ecosystems that are almost entirely independent of the surface. These oases of life stand out in the darkness, their communities dense and diverse compared to the surrounding plains. Life here also interacts with the geological and chemical processes of the deep in ways that blur the line between biology and geology. Microbes in the sediments help regulate the chemistry of the ocean by breaking down organic matter and recycling nutrients. They play a crucial role in the global carbon cycle, converting carbon from the surface into forms that can be stored in the deep ocean for centuries or even millennia. Other microbes influence the cycling of nitrogen, sulfur, and other elements, processes that shape the chemistry of the entire planet. The deep ocean is not just a passive repository for material from above. It is an active engine of biogeochemical transformation, driven in part by the life that thrives within it. Despite its apparent remoteness, the life of Milwaukee Deep is not isolated from the rest of the ocean. Many deep-sea species have larval stages that drift upward into shallower waters, carried by currents before eventually settling back into the depths. This vertical migration connects the hadal zone to the broader ocean ecosystem, allowing genetic exchange between populations and linking deep-sea life to surface processes. Some organisms even undertake regular migrations themselves. Certain fish and invertebrates rise hundreds of meters each night to feed in richer waters before returning to the depths by day. These journeys blur the boundary between surface and deep, showing that even in the black silence of the trench, life is part of a larger, interconnected system. The more we learn about life in places like Milwaukee Deep, the more we realize how little we know. Most of the species found in hadal trenches are still undescribed by science. Each new expedition returns with organisms that defy classification, new species of amphipods, unknown bacteria, mysterious gelatinous creatures unlike anything seen before. Some may represent entirely new branches of the tree of life, their adaptations so extreme that they offer insights into biology itself. Others may hold clues to the origins of life on Earth. The conditions in the hadal zone, high pressure, low temperature, absence of sunlight, are thought to resemble those of the early oceans when life first emerged. Studying how life survives here may help us understand how it began and where it might exist elsewhere in the universe. That possibility is one reason astrobiologists are so interested in the deep ocean. If life can thrive in Milwaukee Deep, where sunlight never penetrates and pressure crushes everything we know, then it may also thrive beneath the icy crust of Europa, one of Jupiter's moons, where a vast ocean lies hidden beneath kilometers of ice. It may exist in the methane seas of Titan, or the subsurface oceans of distant exoplanets. The adaptations that allow life to flourish in the hadal zone, pressure-resistant enzymes, chemosynthesis, slow metabolisms, could be the same adaptations that sustain life in alien oceans. In this sense, the life of Milwaukee Deep is not just a biological curiosity. It is a window into possibilities far beyond our planet. But before we can draw those conclusions, we have to understand this world more fully. That is easier said than done. Studying life in the hadal zone is one of the greatest challenges in science. The pressure destroys most equipment not specifically designed for it. Sampling is difficult, as bringing organisms to the surface often kills them before they can be studied. Even observing life in situ is a challenge, as lights and noise from submersibles can disturb delicate behaviours. Despite these obstacles, advances in technology are making the deep more accessible than ever. Autonomous landers equipped with cameras and sensors can descend to the trench floor and remain there for days or weeks, recording data and collecting samples. Pressure-retaining samplers allow scientists to bring organisms to the surface without exposing them to lethal changes in pressure. Genomic techniques enable the study of microbial communities without the need to culture them in the lab. These tools are revealing a level of diversity and complexity that would have been unimaginable a generation ago. Deep-sea microbial communities are far more varied than previously thought, with thousands of species coexisting in a single gram of sediment. Many of these microbes have metabolic pathways unlike anything seen at the surface, suggesting that life has found solutions to the challenges of the deep that we have yet to understand. Larger organisms, too, show surprising diversity. Even in the relative scarcity of Milwaukee Deep, there are dozens of species of amphipods, multiple types of snailfish, and countless invertebrates adapted to niches we are only beginning to recognize. The hadal zone, once thought to be barren, is emerging as one of the most dynamic and complex ecosystems on the planet. Life here also plays a role in shaping the physical environment. As organisms feed, burrow, and excrete, they alter the structure of the sediments and the chemistry of the water just above them. This bioturbation influences how nutrients are recycled, how gases are exchanged, and how carbon is stored. Over geological timescales, these processes contribute to the formation of sedimentary layers and even influence the stability of the trench walls. Life is not just a passenger in this environment, it is an active participant, shaping the very conditions it depends on. It is humbling to realise that all of this activity, all of this diversity unfolds in a place where sunlight never reaches, where the temperature rarely rises above freezing, and where the pressure would crush a human in an instant. It challenges our assumptions about what life needs and where it can exist. It reminds us that biology is not bound by the conditions we find comfortable. It thrives wherever it can, adapting to extremes that seem impossible from the surface. And it suggests that life, once it emerges, is remarkably difficult to extinguish. The black silence of Milwaukee Deep is not empty. It is full of motion and interaction, of feeding and reproduction, of growth and decay. It is a place where life and geology, chemistry and biology, surface and deep are all intertwined. It is slow and subtle compared to the surface world, but it is no less vital. In fact, it may be more so, because it operates on time scales and in conditions that shape the planet itself. The organisms that live here influence the cycling of elements, the storage of carbon, and the chemistry of the ocean. They are part of the machinery that keeps Earth habitable, even if we rarely think of them. And they remind us too of how much mystery remains. Every descent into Milwaukee Deep reveals something unexpected. A new species, a novel chemical process, a behaviour never seen before. Each discovery deepens our understanding but also expands the horizon of what we do not know. The black silence is not a void to be filled with knowledge. It is a vast dynamic system that will continue to surprise us no matter how much we learn. And it is a system that is intimately connected to the rest of the planet, despite its isolation. The life here depends on the surface, and the surface is shaped by the processes that unfold in the deep. It is all part of the same story, one that stretches from the sunlight zone to the trench floor and beyond. What lies ahead, deeper still in this story, is the hidden machinery that makes this strange world possible. The unseen architects that build and maintain it, the microbial engineers that transform chemistry into life, and the geological forces that set the stage for everything we've seen so far. To understand Milwaukee Deep fully, we have to look beyond the visible organisms and into the invisible processes that sustain them. And that is where our journey leads next, deeper into the hidden workings of the Atlantic's darkest abyss. If there is one lesson the deep ocean teaches over and over, it is that the most powerful forces shaping life are often the ones we cannot see. In the darkness of Milwaukee Deep, the great creatures that capture our imagination, the ghostly snailfish, the giant amphipods, the scavengers that patrol the seafloor, are only the most visible expression of a system that is built from the bottom up. The real work of sustaining life here, of transforming raw chemistry into energy and building the foundation on which every other species depends, is done by organisms so small they are invisible to the naked eye. They are the microbes, bacteria, archaea, and other microscopic life forms. And they are the true architects of the deep. Without them, the trenches would be lifeless. Without them, the slow rain of organic matter from the surface would pile up as inert debris. Without them, the cycles that regulate the chemistry of the ocean and the planet itself would grind to a halt. It is easy to underestimate their importance. On land and in the sunlit sea, we often think of plants as the base of the food web, converting sunlight into chemical energy that supports everything else. In the hadal zone, there are no plants and no sunlight, but the principle is the same. Here, microbes occupy the role of primary producers, not by capturing light, but by harnessing chemical energy from their surroundings. This process, known as chemosynthesis, is the deep ocean's equivalent of photosynthesis. Instead of sunlight, it relies on reactions involving chemicals like methane, hydrogen sulfide, or ammonia, which seep from the seafloor or are produced by the decomposition of organic matter. These reactions release energy that microbes use to build sugars and other organic molecules, which then form the base of the food chain. Chemosynthesis is not a new or rare process. In fact, it may be one of the oldest metabolic pathways on Earth, dating back billions of years to a time before photosynthesis evolved. It is found in deep-sea hydrothermal vent ecosystems, in cold seeps, and in the sediments of hadal trenches like Milwaukee Deep. Here, it sustains dense communities of microbes that thrive in the absence of light. Some of these microbes live freely in the sediment, forming mats on the seafloor. Others live inside the bodies of larger organisms, forming symbiotic relationships that benefit both partners. In either case, they provide the foundation for life in an environment where energy is scarce and must be extracted from the most unlikely sources. Microbes do more than just produce energy. They also drive the recycling of nutrients, breaking down organic matter that drifts down from the surface and converting it into forms that other organisms can use. When a particle of marine snow settles on the seafloor, it is quickly colonized by bacteria that secrete enzymes to digest complex molecules like proteins, lipids, and carbohydrates. These molecules are broken down into simpler compounds, which are then consumed by other microbes or absorbed into the water column. This process, known as remineralization, is essential to the functioning of the deep-sea ecosystems. Without it, nutrients would become locked in organic matter, unavailable to support new growth. Instead, microbial activity ensures that carbon, nitrogen, phosphorus, and other elements continue to cycle through the system, sustaining life even in the deepest trenches. The chemical transformations carried out by microbes are astonishingly diverse. Some species oxidize methane, converting it into carbon dioxide and water. Others reduce sulfate to sulfide, a reaction that not only releases energy, but also influences the chemistry of the surrounding water. Still others fix nitrogen, converting atmospheric nitrogen dissolved in seawater into forms that can be used by living organisms. Each of these processes is part of a vast network of chemical reactions that link the deep ocean to the rest of the planet. Together they regulate the composition of seawater, control the availability of nutrients, and even influence the global carbon cycle. In many ways, the microbes of Milwaukee Deep are more than just inhabitants of their environment. They are its engineers. By altering the chemistry of the sediments and the water, they create conditions that allow other life forms to exist. The buildup of sulfide from microbial sulfate reduction, for example, supports communities of chemosynthetic bacteria and the animals that depend on them. The removal of oxygen from certain layers of sediment creates microhabitats for anaerobic organisms. The fixation of nitrogen ensures a steady supply of this essential element, even in an environment where it is often scarce. Each of these changes ripples outward through the ecosystem, shaping the distribution of species, the flow of energy, and the structure of the community. The influence of microbes extends beyond biology. They also play a role in geological processes, shaping the very landscape of the trench. As they break down organic matter, microbes produce gases like methane and carbon dioxide, which can accumulate in the sediments and escape through seeps on the seafloor. These seeps, in turn, create habitats for specialized communities of microbes and animals. In some cases, microbial activity can even trigger the formation of carbonate minerals, which precipitate out of the water and contribute to the structure of the seafloor. Over time, these processes can influence the stability of sediments, the formation of geological features, and the cycling of elements between the ocean and the crust. Symbiosis between microbes and larger organisms is another crucial part of this story. Many deep-sea animals rely on microbial partners to survive in the extreme conditions of the hadal zone. Some species of polychaete worms, for example, harbour chemosynthetic bacteria in specialised organs, which provide them with energy in exchange for access to chemicals like hydrogen sulfide. Certain bivalves have symbiotic microbes living in their gills, allowing them to thrive in environments where food is otherwise scarce. Even some amphipods host microbial communities on their exoskeletons, which help them process nutrients or detoxify harmful compounds. These partnerships are so integral that neither partner could survive alone. They are examples of how deeply intertwined life is in the deep ocean, even at the smallest scales. The microbes themselves are astonishingly diverse. Genetic studies of hadal sediments have revealed thousands of species, many of which are unknown to science. Some belong to familiar groups, like proteobacteria and bacteroidetes, while others represent entirely new lineages. Their metabolic capabilities are equally varied, reflecting the wide range of chemical environments within the trench. Some are specialists, adapted to thrive on specific compounds like methane or sulfide. Others are generalists, capable of switching between metabolic pathways as conditions change. This diversity ensures that the ecosystem remains resilient in the face of fluctuations in energy supply, chemical composition, and physical conditions. One of the most remarkable aspects of microbial life in the hadal zone is its ability to withstand extreme pressure. At 8,000 meters, the pressure exceeds 800 times that at the surface, enough to crush most cellular structures. Yet these microbes not only survive, but flourish. Their membranes contain unique lipids that remain fluid under pressure. Their enzymes are structured to resist deformation, and their DNA is stabilized by specialized proteins. Some species even require high pressure to function properly, unable to grow in laboratory conditions unless the pressure is artificially increased. These adaptations are not just biological curiosities. They offer insights into the fundamental limits of life and have potential applications in biotechnology, from pressure-resistant enzymes for industrial processes to novel molecules for medicine. The chemical and biological processes driven by microbes do more than sustain life in the trench. They also influence the global climate. The deep ocean is one of the largest reservoirs of carbon on Earth, and microbial activity plays a key role in controlling how much carbon is stored there and how much is released back into the atmosphere. When organic matter sinks from the surface and is buried in sediments, some of it is broken down by microbes and converted into carbon dioxide, which can dissolve back into the water and eventually return to the atmosphere. But some carbon is locked away for thousands or even millions of years, sequestered in the sediments by microbial activity. The balance between these processes, between decomposition and burial, has a direct impact on atmospheric carbon dioxide levels and, by extension, on global climate. Microbes also contribute to the production and consumption of methane, a greenhouse gas far more potent than carbon dioxide. Some species produce methane as a byproduct of their metabolism, while others consume it, oxidizing it into less harmful compounds. The net effect of these processes can vary depending on conditions in the sediments, but over geological timescales, they have a significant influence on the amount of methane that escapes into the ocean and the atmosphere. Understanding these processes is crucial for predicting how the ocean will respond to changes in climate, and how it will, in turn, influence the climate system. The microbial architects of Milwaukee Deep do not work alone. Their activities are influenced by physical and chemical factors that operate on much larger scales. The movement of tectonic plates, for example, creates the trench itself and shapes the flow of fluids through the sediments. These fluids supply the chemicals that fuel chemosynthesis and influence the distribution of microbial communities. The deposition of organic matter from the surface provides the raw material for decomposition and nutrient cycling. The circulation of deep water transports oxygen and other dissolved gases into the trench, affecting the types of metabolism that can occur. Each of these factors interacts with microbial processes, creating a dynamic system that is constantly evolving. This interplay between the microscopic and the planetary is one of the most fascinating aspects of the deep ocean. Processes that unfold on scales of micrometers and milliseconds can influence the chemistry of the entire ocean and, by extension, the climate of the planet. At the same time, geological events like earthquakes and volcanic eruptions can reshape the environment in which microbes live, altering their activity and the processes they drive. The deep ocean is a system in which the smallest and largest scales are intimately connected, and microbes are the bridge between them. The work of these architects is not limited to the present. The sediments of Milwaukee Deep are filled with the remains of ancient microbial communities, preserved as chemical signatures and fossilized structures. These records offer a window into the past, revealing how microbial processes have changed over time and how they have responded to shifts in climate, ocean chemistry, and tectonic activity. They show, for example, how periods of increased organic carbon deposition during interglacial periods fueled greater microbial activity, or how changes in oxygen levels altered the balance between different metabolic pathways. They reveal how microbial life has shaped the ocean for millions of years, and how it has, in turn, been shaped by the changing planet. Even the structure of the trench itself bears the imprint of microbial activity. The formation of certain types of minerals, the distribution of gases within the sediments, and the development of seeps and vents are all influenced by the work of microbes. Over geological timescales, these processes can alter the landscape, creating new habitats and influencing the flow of fluids and chemicals. In this sense, microbes are not just inhabitants of the trench. They are active participants in its creation, shaping its physical and chemical structure in ways that ripple through the entire ecosystem. Despite their importance, the microbial architects of the deep remain among the least understood forms of life on Earth. Many species have never been cultured in the laboratory, and their metabolic pathways are known only from genetic sequences. The interactions between different microbial groups and between microbes and larger organisms are still poorly understood. The rates at which key processes occur and how they vary in space and time are topics of ongoing research. Every new expedition to the Milwaukee Deep brings new discoveries, revealing layers of complexity that challenge our assumptions and expand our understanding. The implications of this research extend far beyond the trench itself. By studying how microbes function under extreme conditions, scientists gain insights into the fundamental principles of life. These insights can inform our search for life on other planets and moons where similar conditions may exist. They can also lead to practical applications, from new biotechnologies to strategies for carbon sequestration. And they deepen our appreciation for the interconnectedness of Earth's systems, showing how processes that unfold in the most remote corners of the planet are linked to the air we breathe, the climate we experience and the future we are shaping. The architects of the deep work silently and invisibly, their activity hidden beneath layers of sediment and darkness. But their influence is everywhere. They sustain the ecosystems of the hadal zone, transform the chemistry of the ocean, shape the geology of the seafloor, and regulate the climate of the planet. They are the foundation upon which everything else depends, the unseen builders of the deep ocean world. And though they are microscopic, their reach extends from the depths of Milwaukee Deep to the highest layers of the atmosphere, from the distant past to the far future. In the end, understanding the deep ocean means understanding these architects. It means looking beyond the visible life and the dramatic landscapes to the invisible processes that make them possible. It means recognizing that the story of Milwaukee Deep is not just about darkness and pressure, not just about strange creatures and geological forces, but about the tiny, tireless organisms that weave those elements together into a functioning whole. And it means realizing that in the most remote and inhospitable corners of our planet, life is not just surviving, it is shaping the world. The work of these unseen builders does not stop. It continues, hour after hour, century after century, turning the raw materials of the earth into the foundation of life. And as we follow their story deeper, we begin to see that the trench is more than a geological feature or a biological curiosity. It is a living system, built and maintained by countless invisible hands, each playing a role in the grand machinery of the planet. And woven into that system are messages from the past, records written not in words but in layers of sediment and chemical traces, messages that tell us where we have been and hint at where we're going. Every layer of sediment at the bottom of Milwaukee Deep is more than just mud and mineral. It's a page in a story that stretches back thousands, even millions of years. A story written not in ink but in particles and molecules, in chemical signatures and fossilized remains. Down here, in the cold and crushing dark, time moves differently. Surface storms rage and fade in hours, seasons pass unnoticed, and even centuries slip by with a little change. But the seafloor remembers. It records everything, the rise and fall of life at the surface, the shifting of continents, the pulses of climate and chemistry that have shaped Earth's history. To study the sediments of the deep ocean is to read those records, to listen to the messages the past has left behind, sealed in the quiet layers of the abyss. These messages arrive grain by grain, delivered by the slow rain of marine snow, by the fall of volcanic ash, by the drift of dust from distant continents. Over thousands of years they accumulate into layers that are thin and delicate but remarkably detailed. A single centimetre of sediment on the trench floor might represent hundreds or even thousands of years. A metre might span entire epochs. Each layer is a snapshot of the world as it was when it formed, capturing the conditions of the ocean, the climate, and even life itself. Together they form an archive unlike any other, one that is continuous, global, and astonishingly precise. One of the most important records preserved in these sediments is that of climate change. The ocean is a central player in Earth's climate system, storing vast amounts of heat and carbon and redistributing them around the globe. Changes in temperature, ice cover, and atmospheric composition all leave their mark on the deep sea. Tiny shells of planktonic organisms, known as foraminifera, settle to the seafloor when they die, becoming part of the sediment. The chemical composition of these shells reflects the conditions of the water in which they lived, the temperature, the salinity, the amount of carbon dioxide. By analysing the isotopes of oxygen and carbon in these fossils, scientists can reconstruct past climates with remarkable accuracy. They can track the advance and retreat of ice ages, the warming of interglacial periods, and the subtle shifts that accompany changes in Earth's orbit and axial tilt. These records reveal a planet that is anything but static. Over the past few million years, Earth has cycled repeatedly between glacial and interglacial states, with ice sheets advancing and retreating across the continents. Each transition left its mark in the sediments of the deep ocean. During glacial periods, colder temperatures and expanded ice sheets altered ocean circulation, reducing the delivery of nutrients and oxygen to the deep. This led to changes in the composition of the sediments, different types of foraminifera, shifts in carbon isotopes, variations in the accumulation of organic matter. During interglacial periods, warmer temperatures and higher sea levels reversed these trends. These patterns, preserved in the mud at the bottom of Milwaukee Deep, provide a continuous record of climate change stretching back millions of years. But the messages recorded in the sediments go beyond climate. They also tell the story of life itself. Microfossils, the remains of tiny organisms like foraminifera, coccolithophores, and diatoms, are abundant in deep-sea sediments, and their diversity and abundance reflect the state of marine ecosystems at the time they lived. Periods of high productivity at the surface, driven by changes in nutrient availability or climate, leave thick layers rich in organic carbon and microfossils. Periods of decline leave thinner, sparser layers. Mass extinction events triggered by volcanic eruptions, asteroid impacts or other catastrophes are marked by abrupt shifts in the composition of microfossil assemblages. These records allow scientists to trace the evolution of life in the ocean, to identify moments of crisis and recovery, and to understand how ecosystems respond to change. One of the most striking examples of this is the Cretaceous-Paleogene boundary, the layer of sediment that marks the mass extinction event 66 million years ago that wiped out the dinosaurs and many other species. This boundary is found in deep-sea sediments around the world, including those in the Atlantic. It is rich in iridium, a rare element associated with asteroids, and it coincides with the sudden disappearance of many microfossil species. Just above it, new species appear, marking the recovery of life in the aftermath of the catastrophe. Layers like this are more than just evidence of events. They are timestamps, precise markers in the geological record that allow scientists to synchronize events across the globe and build a coherent picture of Earth's history. Volcanic eruptions leave their own signatures in the sediments of Milwaukee Deep. Layers of ash, known as tephra, settle through the water and accumulate on the seafloor, sometimes thousands of kilometers from their source. These layers can be dated and matched to specific eruptions, providing a timeline of volcanic activity and its impacts on the ocean and climate. Some eruptions inject vast amounts of sulfur and carbon dioxide into the atmosphere, triggering cooling or warming that leaves its mark in the sediments. Others deliver nutrients to the ocean, stimulating blooms of plankton that increase the flux of organic matter to the deep. Each layer of ash is both a record of a moment of violence and a clue to its consequences. Even the slow, steady processes of erosion and weathering on land leave traces in the deep ocean. Dust carried by winds from deserts like the Sahara can travel thousands of kilometers before settling into the Atlantic. Its composition reflects the climate and vegetation of the regions it came from, providing information about changes on land that might otherwise be lost. Rivers deliver sediments rich in minerals and organic matter, their flow influenced by rainfall, ice melt, and tectonic activity. Together, these inputs record the interplay between land, atmosphere, and ocean over geological time. The sediments also bear witness to the history of the ocean itself, its currents, its chemistry, its structure. Changes in ocean circulation, driven by shifts in climate or tectonics, alter the distribution of nutrients and oxygen, which in turn affect the types of organisms that thrive and the composition of the sediments they leave behind. Variations in the deposition of calcium carbonate reflect changes in the saturation state of the deep ocean, which is influenced by atmospheric carbon dioxide levels. Layers enriched in manganese nodules or other minerals mark periods of altered redox conditions or shifts in the sources of material entering the ocean. Each of these signals is a piece of the puzzle, a clue to how the ocean has evolved and how it has influenced the planet. Not all the messages from the past are ancient. The sediments of Milwaukee Deep also contain records of the past few centuries, a blink in geological time, but a period of profound change. The Industrial Revolution, which began in the 18th century, left a clear chemical signature in the deep ocean. Layers from this period show increases in carbon from fossil fuel emissions, changes in the ratios of stable isotopes, and the presence of pollutants like lead and mercury. Radioactive isotopes from nuclear weapons testing in the mid-20th century provide another unmistakable marker, appearing as sharp peaks in the sedimentary record. Microplastics, which first entered the ocean in significant quantities in the mid-20th century, are now found even in the deepest trenches, their presence a stark reminder of humanity's reach. These modern layers are particularly important because they allow scientists to compare natural variability with human-induced change. By examining how carbon levels, microfossil assemblages, and chemical signatures have shifted over the past few centuries, researchers can separate the effects of natural cycles from those of industrial activity. The results are sobering. The rate of change in many indicators, carbon dioxide concentrations, temperature, the composition of marine ecosystems, is far greater today than at almost any time in the geological record. The sediments of Milwaukee Deep do not just record these changes, they testify to their speed and magnitude, offering a perspective that is difficult to grasp from the surface alone. The messages preserved in the deep are not limited to global-scale events. They also record local phenomena that provide insight into the dynamics of the trench itself. Turbidity currents, underwater avalanches triggered by earthquakes, landslides, or the collapse of sediment on continental slopes, leave distinctive layers of coarse material in the otherwise fine-grained sediments of the trench floor. These layers can be used to reconstruct the history of seismic activity and slope stability in the region. They reveal how often large earthquakes occur, how far their effects reach, and how the landscape of the trench evolves over time. In some cases, they even preserve evidence of ancient tsunamis. Their deposits are a reminder of the power of the forces at work in this seemingly quiet world. Reading these messages is a painstaking process. Sediment cores are collected from the trench floor, often several meters long and just a few centimeters in diameter. Each core is a time capsule, with the youngest sediments at the top and the oldest at the bottom. Scientists slice these cores into thin sections and analyze them layer by layer, using a combination of techniques: microscopy, chemical analysis, radiometric dating, genetic sequencing, to extract information. They examine the microfossils to identify past species and their abundance. They measure isotopic ratios to infer temperature, salinity, and carbon cycling. They look for traces of volcanic ash, pollen, or dust that might point to events on land. Each measurement adds a piece to the story, and together they build a detailed picture of the past. Sometimes the messages in the sediments reveal surprises that challenge our understanding of Earth's history. Layers that show abrupt changes in carbon isotopes, for example, can indicate massive releases of greenhouse gases, perhaps from volcanic activity or the destabilization of methane hydrates, events that may have triggered rapid warming in the distant past. Other layers show sudden declines in microfossil diversity, pointing to mass extinctions or dramatic shifts in ocean chemistry. Still others reveal patterns that repeat on regular cycles, reflecting changes in Earth's orbit and the distribution of sunlight that drive the glacial-interglacial rhythm. Each of these discoveries deepens our understanding of the forces that shape the planet and the ways in which they interact. The messages from the past are not just academic curiosities, they have practical value for the present and the future. By studying how the climate system responded to past increases in greenhouse gases, scientists can improve models that predict future climate change. By understanding how marine ecosystems recovered from past disruptions, they can better anticipate how they might respond to current pressures. By reconstructing the history of seismic activity in regions like the Puerto Rico Trench, they can assess the risks of future earthquakes and tsunamis. The sediments of Milwaukee Deep are not just records of what was. They are tools for understanding what is and what will be. They also serve as a humbling reminder of the planet's vast timescales. A few millimeters of sediment might represent a century. A meter might cover tens of thousands of years. Human history, with all its wars, revolutions and discoveries, is barely a thin smear on this record. The deep ocean has seen ice ages come and go. Continents drift. Species rise and fall, all recorded in its quiet layers. To hold a core of sediment from the trench floor is to hold a timeline of Earth itself, a physical connection to events that unfolded long before humans existed and will continue long after we are gone. And yet, for all the richness of this archive, much of it remains unread. The deep ocean is vast and only a tiny fraction of its sediments have been sampled. Many regions of the trench are completely unexplored, their records untouched. Even where cores have been collected, the resolution of our analyses is limited by technology and time. The sediments hold far more information than we can currently extract, from genetic fragments of ancient organisms to subtle chemical signals that hint at past events we do not yet understand. Each new technique, from improved radiometric dating to advanced DNA sequencing, opens new windows into this archive, revealing details that were previously invisible. The messages from the past are still arriving. Marine snow continues to fall, dust still drifts from distant deserts, rivers still carry sediments into the sea. Layer by layer, the archive grows, recording the world as it is today for future generations to read. And just as we now study the sediments of ancient oceans to understand past climates and ecosystems, future scientists will study the layers forming now to understand our time. They will see the sharp chemical shifts of the industrial era, the surge in carbon dioxide, the spread of microplastics. They will see the fingerprints of our actions written into the fabric of the ocean, and they will judge the consequences just as we now judge those of past events. The seafloor of Milwaukee Deep is, in this way, both a record and a witness. It remembers everything: the drift of continents, the fall of meteorites, the eruption of volcanoes, the rise and fall of species, the imprint of human industry. It is a silent observer, indifferent to the passage of time but endlessly patient in its accumulation of memory. And in that patience lies a profound lesson. The world changes. It always has. But those changes are recorded, remembered, and preserved, grain by grain, layer by layer, deep beneath the surface. As we turn from the past toward the present, those layers remind us that the deep ocean is not just a repository of memory, but a living system that continues to respond to the forces of the surface. The same sediments that hold the story of ancient ice ages also contain evidence of modern pollution. The same chemical cycles that shaped the ocean millions of years ago continue to operate today, influenced now by human hands. And the same geological forces that carved the trench in the distant past are still at work, reshaping the sea floor and influencing the world above. The messages from the past are not isolated. They are part of a continuous story, one that extends into the present and shapes the future. And as we continue to explore this world, we find that listening to the past is not enough. We must also learn to listen to the present, to the subtle signals that reveal how the deep ocean is changing now, to the tools and technologies that allow us to hear its hidden rhythms, to the ways in which the abyss communicates its state to those who know how to listen. Because the deep does speak, not in words or sounds we recognize, but in patterns of movement, in vibrations, in chemical whispers that travel through the water and the rock. And if we learn to listen, those messages can tell us not only where we have been, but where we are headed. Reaching the bottom of Milwaukee Deep is only the first step toward understanding it. Being there, or even sending a machine there, is not the same as truly knowing what goes on in the darkness. The trench is vast, silent, and inaccessible, a place that resists our usual methods of observation. Sunlight cannot reach it, so satellites and cameras are blind. Radio waves do not penetrate seawater, so communication is difficult. Pressure crushes most instruments long before they get close. If we want to study the hadal zone, we must learn to listen to it on its own terms. That means finding ways to sense its hidden processes, to detect the faint signals that ripple through its water and sediments, to read the language of the abyss itself. Listening to the deep is both a technological challenge and a philosophical shift. For centuries, humans explored the ocean in ways that mirrored our exploration of land. By travelling through it, mapping its surface, collecting samples, and observing directly with our eyes. But the deep ocean does not lend itself to such approaches. Its darkness hides everything from view, and its pressures make direct exploration costly and rare. Instead, scientists have learned to infer what is happening down there from the signals that reach us indirectly. These signals take many forms: sound waves that travel through the water, chemical traces carried upward by currents, seismic vibrations that pass through rock, even faint shifts in gravity. Each is a piece of information, a clue to the dynamics of a world we cannot see. Sound is one of the most powerful tools we have. Water is an excellent medium for transmitting sound, and low-frequency waves can travel thousands of kilometers through the ocean without significant loss of energy. Marine animals have long exploited this property, using sound to communicate, navigate, and hunt in the darkness. Humans do the same. Sonar, short for sound navigation and ranging, is the cornerstone of deep-sea exploration. Active sonar systems emit pulses of sound and measure the echoes that bounce back from the sea floor, allowing scientists to map the shape of trenches like the Puerto Rico Trench with extraordinary precision. These maps reveal the contours of the seafloor, the steepness of trench walls, the presence of ridges, canyons, and faults. They show where sediments have accumulated and where landslides have occurred. Without sonar, much of what we know about Milwaukee Deep's geography would remain a mystery. Passive acoustics, the art of listening rather than transmitting, provides another window into the deep. The abyss is not as silent as it seems. The movement of tectonic plates produces low, rumbling sounds that can be detected thousands of kilometers away. Earthquakes generate sharp, powerful pulses that reverberate through the water and the rock below. The slow settling of sediments, the collapse of underwater landslides, and the movement of fluids through the seafloor all create their own acoustic signatures. Even biological activity contributes to the soundscape. The calls of deep-diving whales, the clicks and pulses of squid, the faint crackle of crustaceans moving across the seafloor, all are part of the acoustic environment of the deep ocean. By deploying hydrophones, underwater microphones, scientists can record these sounds and use them to infer what is happening far below. Some of the most intriguing discoveries in deep ocean acoustics have been unexpected. Hydrophones placed in deep trenches have detected mysterious sounds that defy easy explanation. Long, low-frequency moans, sharp, percussive bursts, and complex patterns of clicks and pulses. Some of these may be geological, produced by shifting rock or the movement of fluids deep within the earth. Others are likely biological, the calls of species we have never encountered. A few remain unexplained, their origins unknown. Each sound is a clue, a piece of information about a world we cannot see. And as our acoustic technology improves, our ability to decode these signals grows, revealing the deep as a place not of silence, but of constant, subtle activity. Sound is not the only way the abyss communicates. Chemical signals provide another avenue of investigation. Water from the trench slowly mixes with water from above, carrying with it traces of the processes that occur in the depths. By sampling and analysing this water, scientists can detect the products of microbial activity, the signatures of chemical reactions, and the presence of dissolved gases like methane or hydrogen sulfide. These chemical traces reveal information about the metabolism of deep-sea ecosystems, the cycling of elements, and the dynamics of fluid flow through sediments and rock. They also provide clues about geological processes, such as the release of fluids from subducting plates or the formation of cold seeps on the seafloor. Sediment cores, too, carry chemical messages from the abyss. The composition of pore water, the water trapped between grains of sediment, reflects the balance of microbial processes occurring within. Gradients in dissolved oxygen, nitrate, sulfate, and methane reveal the depth and intensity of different metabolic pathways. Variations in isotopic ratios can indicate changes in carbon cycling or the sources of organic matter. Even trace metals and rare earth elements can provide insights into the movement of fluids and the geochemical evolution of the trench. Each of these signals is subtle, requiring careful measurement and interpretation, but together they paint a picture of a dynamic environment shaped by both biological and geological forces. Seismic signals offer yet another perspective. The Puerto Rico Trench is a tectonically active region, formed by the subduction of the North American plate beneath the Caribbean plate. This process generates earthquakes, some of which are powerful enough to trigger tsunamis. By deploying seismometers on the seafloor and on land, scientists can monitor these events and study how energy moves through the Earth's crust. The seismic waves that pass through the trench carry information about its structure, the thickness of sediments, the composition of underlying rock, the presence of faults and fractures. They also reveal how the trench responds to stress, how it stores and releases energy, and how it might behave in the future. Seismic monitoring is not just a scientific tool but a practical one, essential for assessing hazards in regions vulnerable to tsunamis and earthquakes. Gravity and magnetism, though less obvious, also help us listen to the deep. Variations in the Earth's gravitational field can reveal differences in the density and thickness of the crust beneath the trench. Magnetic anomalies can indicate the presence of specific rock types or the history of seafloor spreading and tectonic movement. Together, these measurements provide context for the biological and chemical processes occurring above. They show how the structure of the trench influences fluid flow, how geological features shape microbial habitats, and how the deep ocean fits into the broader system of Earth's crust and mantle. The tools used to capture these signals are as varied as the signals themselves. Hydrophones are anchored to the seafloor or suspended in the water column, listening for months or years. Autonomous underwater vehicles, AUVs, and remotely operated vehicles, ROVs, carry sensors that measure temperature, salinity, chemical composition, and current speed. Landers, free-falling platforms that sink to the seafloor and return to the surface after completing their missions, can deploy instruments, collect samples, and record video. Pressure-retaining samplers capture water and organisms without exposing them to the lethal changes in pressure that occur during ascent. Each of these tools is a way of extending our senses into a world where our bodies cannot go. Listening to the abyss is not just about collecting data, it is about interpreting it, finding patterns in the noise, and connecting signals to processes. A sudden burst of low-frequency sound might indicate an earthquake, or the collapse of a slope triggered by sediment buildup. A spike in methane concentration could be a sign of microbial activity, or the release of gas from destabilized hydrates. A shift in isotopic ratios might reflect a change in carbon cycling, or the arrival of organic matter from a distant bloom at the surface. Every signal has multiple possible explanations, and teasing them apart requires not only data but context. Knowledge of ocean currents, sediment dynamics, tectonic processes, and biological activity. It requires an understanding of how all these elements interact to shape the deep ocean. This challenge is compounded by the sheer scale of the abyss. The Puerto Rico Trench alone stretches more than 800 kilometers, and Milwaukee Deep is just one part of it. Deploying instruments across such vast areas is difficult and expensive. Communication with deep-sea instruments is slow and limited, often requiring them to store data for months before surfacing. Power is another constraint, as most instruments rely on batteries that eventually run out. These limitations mean that much of what happens in the trench goes unobserved. Our listening is partial and intermittent. a series of snapshots rather than a continuous stream. Despite these challenges, our ability to listen is improving. Advances in technology are expanding the range and resolution of our observations. Fibre optic cables laid on the seafloor can transmit seismic and acoustic data in real time, turning thousands of kilometres of cable into sensors. New generations of AUVs can travel farther and operate longer, mapping and sampling with unprecedented detail. Machine learning algorithms are helping scientists sift through vast datasets, identifying patterns that would be impossible to detect manually. Even satellites, which cannot see the deep directly, contribute by measuring subtle changes in sea surface height that reflect variations in seafloor topography. Together, these innovations are transforming our ability to hear the deep and understand what it is telling us. Listening is not just about science, it is also about humility. The deep ocean speaks in ways that are subtle and often unfamiliar. It does not reveal its secrets easily. Its signals are faint, its patterns complex, its language foreign. Learning to listen means accepting that we will not always understand what we hear, that some signals will remain mysterious, that some patterns will elude explanation. It means embracing uncertainty as part of the process, recognizing that knowledge grows not from having all the answers, but from asking better questions. It also means acknowledging that our presence changes what we hear. The sounds of ships, the rumble of drilling, the explosions of seismic surveys, all these human noises penetrate the deep, altering the acoustic environment and potentially affecting the organisms that rely on sound to communicate and navigate. The chemicals we release into the atmosphere and ocean change the composition of deep water, altering the signals we detect. Even our scientific instruments, with their lights and vibrations, can disturb the systems they are meant to observe. Listening to the abyss requires not only technology but care, a recognition that observation is not neutral, and that our actions have consequences even in the most remote places. The value of listening extends far beyond curiosity. The signals from the deep hold information that is crucial for understanding and protecting the planet. Seismic data help us assess earthquake risk and anticipate tsunamis. Chemical measurements reveal how the ocean is absorbing carbon dioxide and how that might change in the future. Acoustic monitoring can track the movements of marine animals, shedding light on migration patterns and population health. Long-term observations of deep ocean conditions provide early warnings of changes in circulation, oxygen levels, or nutrient availability that could have far-reaching consequences for climate and ecosystems. Listening to the deep is not just an academic exercise, it is a vital part of how we monitor and manage the Earth system. It also has the power to change how we see ourselves. The signals from Milwaukee Deep remind us that we are part of a larger planetary system, one that operates on scales of space and time far beyond our daily experience. They show us that the deep ocean is not an isolated abyss, but an active, dynamic part of the Earth, connected to the surface, the atmosphere, and the solid planet below. They reveal how processes that unfold silently in the darkness shape the world we live in, how earthquakes at the trench create tsunamis that reach distant shores, how microbial activity influences the climate, how deep currents drive the circulation that regulates global temperature. Listening to the deep is a way of listening to the planet itself, and in that listening, there is a kind of dialogue. The abyss speaks, not in words but in waves and vibrations, in chemical gradients and isotopic ratios, in the slow settling of sediments and the sudden violence of tectonic shifts. We respond with our instruments and analyses, with our questions and our models. We try to translate its language into something we can understand, something we can use to guide our actions, and with each step we come a little closer to understanding not just the deep ocean, but the planet as a whole, its history, its dynamics, and its future. The work of listening is far from finished. Much of the abyss remains silent to us, not because it is silent in reality, but because we have not yet developed the tools to hear it. Signals are missed, data are incomplete, interpretations are uncertain. But every new hydrophone, every new sampler, every new algorithm brings us closer. The more we listen, the more we realise that the deep is not a void but a conversation, one that has been going on for billions of years and will continue long after we're gone. And as we listen more closely, we begin to hear something else as well, the faint echoes of our own presence. Our activities at the surface, the carbon we release, the noise we generate, the chemicals we spill, are now part of the abyss's language. They're woven into its acoustic landscape, its chemical signals, its sedimentary record. They're reminders that we are not separate from this world, but part of it, that our actions resonate far beyond where we can see or feel. Listening to the abyss means listening not only to the earth, but to ourselves. This awareness brings responsibility. The deep ocean is vast and resilient, but it is not invulnerable. Its processes are slow, its systems delicate. Disturbances that might seem insignificant on the surface can persist for centuries in the depths. Noise can disrupt communication among animals. Pollution can alter microbial communities and chemical cycles. Climate change can shift circulation patterns and oxygen levels in ways that ripple through the system. Listening teaches us about these vulnerabilities. It shows us where the system is strong and where it is fragile, and it gives us the knowledge we need to act wisely, to protect a world we are only beginning to understand. As we refine our ability to listen, we also refine our sense of wonder. The abyss is not empty. It is alive with signals, rich with stories, filled with rhythms and patterns that speak of forces both ancient and ongoing. It hums with the slow pulse of tectonic movement, whispers with the chemical breath of microbes, sings with the distant calls of whales that dive into its depths. To listen is to connect with something vast and profound, something that existed long before us and will endure long after. It is to hear the heartbeat of the planet, steady and patient beneath the noise of our brief moment on its surface. And it is to realise that this heartbeat is not isolated. It is linked to everything, to the winds that stir the surface, to the rivers that carry sediments to the sea, to the volcanoes that build mountains and shape continents. It is part of a system that includes us, our actions, our future. The abyss is not an alien world, not separate from the rest of Earth. It is Earth, ancient, dynamic, interconnected. And by listening to it, we listen to ourselves in a deeper, broad context. The signals from the deep do not end when we stop measuring them. They continue, indifferent to our attention, part of the ceaseless rhythms of the planet. And if we follow them, if we trace them backward and forward through time, they lead us not only to an understanding of how the abyss works, but to a deeper appreciation of how we fit into the system it sustains. They show us that the ocean is not just water, but memory, not just depth, but connection, and they point us toward the next part of the story, the ways in which our presence reaches even here, the ways we have left our mark on this ancient hidden world, and the ways the abyss responds to that mark in turn. For most of human history, the deep ocean seemed beyond our reach. Too remote, too dark, too hostile to be touched by anything we did at the surface. It was the realm of myths and imagination, a place so far removed from our daily lives that it barely seemed part of the same planet. Even as we learned to sail across the seas, map coastlines and harvest fish from shallower waters, the abyss remained a mystery. It was easy to believe that whatever happened there was governed entirely by nature, untouched by human hands, but that belief no longer holds. The deep ocean, including the very bottom of Milwaukee Deep, now bears unmistakable traces of our presence. Our influence reaches even here, subtle in some ways, overwhelming in others, woven into the chemistry, biology and geology of a world that was once beyond our grasp. The most obvious signs of our reach are physical: microplastics, fragments of synthetic polymers that break down from larger pieces of plastic waste, are now found in sediments throughout the deep ocean. They are in the mud of the Puerto Rico Trench, in the guts of amphipods that live nearly 9 kilometers below the surface, and in the tissues of fish that have never seen daylight. These particles arrive from the surface as part of the same slow rain that delivers marine snow, drifting down over weeks or months until they settle on the seafloor. They do not break down easily. Instead, they accumulate layer upon layer, forming a new kind of geological record, one that future scientists may use to mark the Anthropocene, the era defined by human impact. The presence of microplastics is not just a curiosity, it has consequences for the deep-sea ecosystem. Tiny particles can be ingested by organisms that mistake them for food, clogging digestive systems, reducing feeding efficiency, and exposing them to harmful chemicals. Larger animals that eat these smaller creatures accumulate plastics in their own tissues, passing them up the food chain. Even microbes are affected, colonizing plastic surfaces and altering their metabolic activity in ways that can change nutrient cycling. Over time, the accumulation of plastics may alter the composition of sediments, the structure of microbial communities, and the flow of energy through the ecosystem. It is a new and unplanned layer of the deep-sea environment, one that did not exist a century ago. Plastics are only one part of the story. Chemical pollutants have also made their way into the abyss. Industrial processes, agriculture, mining, and combustion release a wide range of substances into the air and water, many of which eventually find their way into the ocean. Persistent organic pollutants like polychlorinated biphenyls, PCBs, banned decades ago but still present in the environment, have been detected in deep-sea sediments and in the tissues of trench-dwelling organisms. Heavy metals such as mercury and lead, released by burning fossil fuels and industrial activity, also accumulate in the deep. These contaminants do not degrade easily. Instead, they cycle through the food web, concentrating in organisms over time and potentially disrupting physiological processes, reproductive success, and population dynamics. The deep ocean is not immune to radioactive contamination either. Fallout from nuclear weapons testing in the mid-20th century left a distinctive signature of isotopes such as cesium-137 and plutonium-239 in sediments around the world. These isotopes have been detected in the Puerto Rico Trench, far from any test site, carried by ocean currents and incorporated into marine snow. Their presence provides a clear timestamp in the sedimentary record, but it also raises questions about the long-term effects of radioactive materials on deep-sea ecosystems. The half-lives of some isotopes are measured in decades or centuries, meaning they will persist in the environment for generations to come. Even substances we do not think of as pollutants can have far-reaching effects when introduced in large quantities. Carbon dioxide from burning fossil fuels dissolves into seawater, where it reacts to form carbonic acid. This process, known as ocean acidification, lowers the pH of seawater and reduces the availability of carbonate ions, which many marine organisms use to build shells and skeletons. While acidification is most pronounced in surface waters, its effects are not confined there. Over time, changes in surface chemistry propagate into the deep, altering the conditions in which deep-sea organisms live and affecting the stability of minerals in sediments. Acidification can also influence microbial activity, changing the rates of key chemical reactions and altering the balance of carbon cycling in the deep ocean. Climate change, too, casts a long shadow over the abyss. As the planet warms, surface waters heat up and become less dense, which can slow the circulation of deep water that brings oxygen and nutrients into the depths. Reduced circulation can lead to declining oxygen levels in some regions, creating conditions that stress or kill organisms adapted to more oxygen-rich environments. Warming also affects the stability of methane hydrates, crystalline structures of water and methane that form under high pressure and low temperature in deep-sea sediments. As temperatures rise, these hydrates can destabilize, releasing methane into the water column and potentially amplifying global warming. The effects of climate change are complex and far-reaching, and the deep ocean is not immune to them. Our influence reaches the deep not just through what we release, but through what we take. Deep-sea fishing, once limited by technology and cost, now targets species that live hundreds or even thousands of meters below the surface. Some of these species, like the orange roughy, live for more than a century and reproduce slowly, making them vulnerable to overfishing. The removal of large numbers of these fish can disrupt deep-sea food webs and alter the balance of ecosystems. Bottom trawling, a technique that drags heavy nets across the seafloor, causes even more direct damage. It destroys habitats, stirs up sediments, and kills non-target species. The scars of trawling can persist for decades, visible in sonar maps as gouges and furrows in the seafloor. Mining is another looming threat. As demand for metals like cobalt, nickel, and rare earth elements grows, companies are turning their attention to the mineral-rich nodules and crusts found on the deep sea floor. Mining these resources would involve large-scale disturbance of sediments, creating plumes that could spread over vast areas and smother organisms. It could release stored carbon, alter chemical cycles, and disrupt habitats that have taken millennia to form. The full consequences of deep-sea mining are not yet known, but scientists warn that they could be profound and long-lasting, particularly in fragile environments like trenches. Noise is a more subtle but pervasive form of pollution. Ships, drilling operations, and seismic surveys generate low-frequency sounds that can travel great distances through the ocean. These sounds can interfere with the communication and navigation of marine animals, many of which rely on sound in the darkness of the deep. Some species may abandon important habitats in response to chronic noise. Others may suffer physiological stress or disorientation. The full impact of noise on deep-sea ecosystems is not well understood, but it is increasingly clear that the ocean is becoming a noisier place, and that this noise penetrates even into the deepest trenches. All these impacts, plastics, chemicals, carbon, fishing, mining, noise, are cumulative. They interact with one another in ways that are often difficult to predict. Pollutants can weaken organisms, making them more vulnerable to other stresses. Climate change can exacerbate the effects of acidification, deoxygenation, and habitat loss. Disturbance from trawling or mining can release stored contaminants into the water column, amplifying their effects. The result is a complex web of pressures that can alter deep-sea ecosystems in profound ways, and because processes in the deep ocean are slow, recovery from disturbance can take centuries if it occurs at all. The presence of human influence in the deep also changes the way scientists approach their work. In the past, the deep ocean was studied primarily as a natural system, shaped by geological and biological forces operating over vast timescales. Today, it must also be studied as a human-influenced system, one in which natural and anthropogenic processes are intertwined. Understanding the deep now requires not only knowledge of geology, chemistry and biology, but also an awareness of policy, economics, and technology. It requires collaboration between scientists, governments, industry, and the public to balance exploration and exploitation to protect ecosystems while meeting human needs. Despite the scale of our impact, the deep ocean retains remarkable resilience. Many deep-sea species have survived dramatic changes in the past, shifts in climate, chemistry, and sea level that dwarf anything humans have yet caused. Microbial communities can adapt to new conditions, evolving new metabolic pathways to exploit novel energy sources. Sediments can absorb and bury contaminants, removing them from the water column. Over time, physical processes like sedimentation and circulation can dilute or disperse pollutants. But resilience has limits. The rate and magnitude of change today are unprecedented in many ways, and the capacity of deep-sea systems to adapt is not infinite. Some changes may push these systems beyond thresholds from which they cannot recover. The realization that our actions reach even here into the deepest parts of the ocean has profound implications for how we see ourselves and our responsibilities. It challenges the notion that there are places on Earth untouched by humanity. It forces us to confront the reality that our industrial activities, our consumption, and our waste have consequences that extend far beyond what we see. It reminds us that we are not separate from the natural world but part of it, embedded in the same systems we're altering. And it suggests that protecting the deep ocean and the planet as a whole is not just a matter of preserving remote environments, but of safeguarding the interconnected systems that sustain life. This understanding is shaping new approaches to ocean governance. International agreements like the United Nations Convention on the Law of the Sea provide a framework for managing activities in areas beyond national jurisdiction, including the deep ocean. Efforts are underway to establish marine protected areas that include hadal environments, safeguarding biodiversity and ecological function. Regulations are being developed to govern deep-sea mining, with requirements for environmental impact assessments and monitoring. Scientists are advocating for precautionary approaches, arguing that we should not disturb ecosystems we do not yet fully understand. These efforts are complex and contentious, balancing competing interests and uncertainties, but they reflect a growing recognition that the deep ocean is not beyond our responsibility. They also reflect a deeper shift in our relationship with the ocean, a shift from seeing it as a limitless resource to recognizing it as a finite, fragile system. For centuries, the ocean seemed too vast to be affected by human activity. We dumped waste into it, extracted resources from it, and assumed it would absorb whatever we did. The discovery of human impacts in places like Milwaukee Deep shatters that illusion. It shows that the ocean is not limitless, that its capacity to absorb change is finite, and that our actions have consequences even in the most remote corners of the planet. It is a humbling realization, but also an empowering one. If our influence reaches this far, so too can our care and stewardship. In many ways, the human shadow in the deep ocean is a mirror. It reflects our ingenuity and our destructiveness, our capacity for exploration and exploitation, our short-sightedness and our potential for foresight. It shows us what we have done, both intentionally and unintentionally, and invites us to decide what we will do next. Will we continue to treat the deep as a dumping ground, a storehouse of resources, a frontier to be conquered? Or will we approach it with humility and caution, recognizing its complexity, its value, and its vulnerability? Answering that question requires more than technology or policy. It requires a shift in perspective, a recognition that the deep ocean is not a separate world, but part of the same system that sustains us. It requires us to see the connections between our daily lives and the distant trench, between the carbon we emit and the currents that circulate through the abyss, between the waste we produce and the sediments that settle on the seafloor. It requires us to listen to the signals from the deep and to respond with care. The human shadow is already part of the deep ocean story. It is written into the sediments, woven into the chemistry, embedded in the biology. It is a chapter that will persist for millennia, long after the details of our civilizations have faded. But the shape of that chapter, whether it is one of destruction or of stewardship, of harm or of healing, is not yet fixed. It is still being written, grain by grain, decision by decision. And as we consider what that chapter might look like, we might find guidance in the deep itself. The systems that operate here are slow but enduring, resilient but sensitive. They teach us that balance is possible but must be maintained, that disturbances can be absorbed but not indefinitely, that complexity is both a source of strength and a source of vulnerability. They remind us that life and geology, chemistry and biology are intertwined, and that actions taken in one part of the system ripple through the whole. The story of our shadow is not the end of the deep ocean story. It is part of a much larger narrative, one that stretches back billions of years and will continue long after we are gone. That narrative includes not only the scars we leave but the lessons we learn, not only the harm we cause but the possibilities we create. It includes the potential for renewal, for restoration, for a relationship with the ocean that is defined not by exploitation but by respect. And it points toward the deeper questions that the abyss forces us to confront. Questions about resilience, about mystery, about what it means to live on a planet shaped by forces both vast and delicate. These questions do not have easy answers, but they are worth asking, because they lead us to think not just about what we take from the ocean, but what we owe to it. They lead us to see the deep not as a distant, alien place, but as part of our shared home. And they prepare us to explore not only the consequences of our actions, but the lessons the abyss has to offer. Lessons about endurance, about adaptation, about the delicate balance that sustains life even in the most extreme environments. If you spend enough time thinking about Milwaukee Deep, about the crushing pressure, the perpetual darkness, the strange forms of life that thrive there, the layers of memory buried in its sediments, and the traces of humanity that now mingle with its oldest stories, one realization begins to surface again and again. This place is not just an object of curiosity, it is a teacher. It reveals truths about the planet and about ourselves that are easy to overlook from the surface. It shows us how the Earth works at its most fundamental levels, how life adapts and endures, how systems evolve over time, and how everything, from the smallest microbe to the largest tectonic plate, is connected. The lessons of the abyss are not abstract or distant. They are deeply relevant to the challenges we face and to the way we think about our place on this planet. One of the first lessons the abyss teaches is about resilience. Life in Milwaukee Deep exists at the edge of what is physically possible. Pressures more than 800 times those at the surface would crush most organisms in an instant. Temperatures hover just above freezing, sunlight never penetrates, food is scarce and unpredictable, and yet life not only survives, but thrives. Microbes carry out complex chemical reactions under conditions that would destroy enzymes elsewhere. Snailfish glide effortlessly through pressures that would collapse a submarine hull. Amphipods endure months without food, slowing their metabolisms to a crawl until the next morsel drifts down from above. These organisms are not exceptions. They are evidence of life's ability to adapt, to find solutions to seemingly insurmountable challenges. This resilience is not about brute strength. It is about flexibility, about finding ways to work with the conditions rather than against them. Enzymes evolve to remain functional under high pressure. Cell membranes incorporate lipids that stay fluid in the cold. Metabolic pathways shift to exploit the energy sources available. Reproductive strategies change to maximize survival in a world where offspring are few and far between. Each adaptation is a small adjustment, a subtle shift that makes life possible. And together they show that resilience is not about resisting change, but embracing it, about finding ways to persist even when the environment is hostile and the odds are long. There is a lesson here for us too. As the planet warms, as ecosystems shift, as the conditions of our world change in ways we cannot fully predict, resilience will be essential, not just for other species, but for humanity itself. The deep shows us that resilience is possible even under extreme conditions, but it also shows us that it requires time, diversity, and flexibility. The organisms of Milwaukee Deep did not adapt overnight. Their abilities are the result of millions of years of evolution, of countless experiments and refinements. They thrive because their ecosystems are diverse, because they contain a wide range of strategies and solutions. They endure because they are flexible, able to shift and change as conditions demand. If we want to build resilience into our societies and systems, we must learn from these lessons. We must embrace diversity, encourage innovation, and allow time for adaptation to occur. Another lesson the abyss teaches is about interconnection. From the surface, the deep ocean seems isolated, a distant realm with little influence on our daily lives. But the more we study it, the more we realise how deeply connected it is to everything else. The rain of marine snow that feeds life in Milwaukee Deep begins as sunlight captured by phytoplankton at the surface. The oxygen that dissolves into its waters is carried there by currents that circle the globe. The sediments that blanket its floor contain dust from distant deserts, pollen from vanished forests, and ashes from ancient eruptions. Even the chemical composition of its water reflects the composition of the atmosphere above. Every part of the system is linked to every other, and changes in one place ripple through the whole. This interconnection is not just physical, it is biological and chemical, geological and climatic. Microbial processes in the deep ocean influence the global carbon cycle, affecting how much carbon dioxide remains in the atmosphere and how much is stored in sediments. The circulation of deep water redistributes heat and nutrients, shaping climate and sustaining life at the surface. Tectonic processes that build trenches also generate earthquakes and tsunamis that impact coastal communities. Human activities, from burning fossil fuels to releasing pollutants, alter the chemistry of the deep, which in turn affects the processes that regulate the climate. The abyss is not a separate world. It is part of a vast interconnected system that includes the air we breathe, the food we eat, and the climate we depend on. Recognizing this interconnection changes the way we think about environmental challenges. It reminds us that actions taken in one part of the system have consequences elsewhere. Carbon emitted from a factory smokestack affects not only the atmosphere, but also the chemistry of the deep ocean. Plastic discarded on a city street can end up in the sediments of Milwaukee Deep. Changes in ocean circulation triggered by warming at the surface can alter nutrient availability thousands of meters below. Solutions too must be systemic. Addressing climate change, pollution, or biodiversity loss cannot be done in isolation. It requires an understanding of the links between systems and the feedbacks that connect them. The deep teaches us that the boundaries we draw between ocean and land, atmosphere and water, human and natural, are artificial. The planet does not recognize them, and neither should we. The abyss also teaches us about time. At the surface, we measure time in hours, days, and years. We think in terms of human lifespans, political cycles, quarterly profits. The deep ocean operates on different scales. Sediments accumulate at a rate of millimeters per millennium. Currents circulate over centuries. Geological processes unfold over millions of years. Even biological processes are slower here. Growth is measured in decades, reproduction in centuries. To study the deep is to confront a timescale that dwarfs our own, to recognize that many of the processes that shape the planet unfold too slowly for us to witness directly. This perspective is both humbling and instructive. It reminds us that the changes we make today, the carbon we release, the pollutants we spread, the habitats we destroy, will echo for centuries or longer. It shows us that recovery too is slow. A trawl scar on the seafloor may persist for decades. A contaminant buried in sediment may remain for millennia. The deep is patient, but it is not quick to heal. Understanding this helps us see the urgency of acting before damage occurs. It teaches us that prevention is far more effective than restoration, and that short-term thinking is ill-suited to long-term challenges. Time in the deep also offers a different kind of lesson, one about perspective. The sediments of Milwaukee Deep contain records of ice ages and mass extinctions, of volcanic eruptions and asteroid impacts. They show that the planet has endured upheavals far greater than anything we have yet caused, and that life has persisted through them all. This does not excuse inaction or minimize the severity of our current crises, but it does place them in context. It shows that change is a fundamental feature of Earth, that stability is temporary, and that resilience is built not by resisting change but by adapting to it. It encourages us to think beyond the immediate, to consider the legacy we are leaving not just for the next generation, but for the next 100 or 1,000 generations. The deep also teaches us about limits. Every system has them. There is a limit to how much carbon the ocean can absorb, a limit to how much disturbance ecosystems can tolerate, a limit to how quickly species can adapt. In the past, these limits were rarely tested because changes occurred slowly and the planet had time to adjust. Today, human activities are pushing many systems toward, and in some cases beyond, their limits. The consequences of crossing those thresholds are uncertain, but they could be profound and irreversible. The collapse of ice sheets, the release of methane from hydrates, the disruption of deep ocean circulation. Each of these could trigger cascading effects that reshape the planet in ways we cannot fully predict. The abyss shows us that respecting limits is not a constraint but a necessity. It is a lesson written into the structure of every ecosystem and every geological process. Life in Milwaukee Deep exists within narrow bounds of pressure, temperature, and chemistry. Push beyond those bounds, and it fails. The same is true for the planet as a whole. Our challenge is to recognize where those limits lie and to live within them, to design our societies and economies in ways that do not exceed the capacity of Earth's systems to sustain them. This requires restraint, foresight, and humility, qualities that do not always come easily, but that the deep shows us are essential. Humility is itself one of the deepest lessons the abyss offers. The scale of Milwaukee Deep, the complexity of its systems, the timescales over which it operates, all of these dwarf human experience. They remind us that we are a small part of a much larger story, that the planet does not revolve around us, and that our knowledge is limited. Even after decades of exploration, we have mapped only a fraction of the deep ocean. Most of its species remain unknown. Many of its processes are poorly understood. Surprises await in every expedition, challenging our assumptions and expanding our understanding. The deep teaches us to approach the unknown not with arrogance but with curiosity, to accept uncertainty as part of discovery, and to recognize that there is always more to learn. Humility also extends to our sense of control. The abyss reminds us that we do not command the planet. We influence it profoundly and often destructively, but we do not control it. Tectonic plates shift regardless of our desires. Ocean currents flow according to laws of physics we cannot alter. Microbial processes unfold on timescales and in ways we cannot dictate. Our role is not that of a master, but of a participant, one species among many in a complex system that operates according to its own rules. Accepting this does not mean surrendering to fate. It means acting with awareness of our place in the system and with respect for the forces that sustain it. Another lesson the abyss offers is about hiddenness, about the fact that the most important processes are often invisible. The architecture of Milwaukee Deep is shaped not by dramatic events but by slow, continuous forces. The accumulation of sediments, the movement of tectonic plates, the activity of microbes. These processes are easy to overlook because they happen out of sight and over long periods. Yet they are the foundation of everything else. Without them, there would be no trench, no ecosystems, no record of the past. The same is true elsewhere. Many of the systems that sustain human life, the cycling of nutrients, the formation of soil, the flow of groundwater, are invisible in our daily lives. We ignore them at our peril. Recognizing the importance of hidden processes changes how we approach the world. It teaches us to look beyond what is immediately visible, to value what is slow and subtle, and to account for what we do not see. It suggests that solutions to our problems may not lie in dramatic interventions, but in understanding and supporting the underlying systems that make life possible. It encourages us to be attentive to small changes, to listen for faint signals, and to act before those signals become crises. The abyss also offers a lesson in continuity. It shows us that the past, present, and future are not separate but connected, that the events of today become the sediments of tomorrow. The layers of Milwaukee Deep record ancient climates and mass extinctions, but they also record the rise of industrial society, the spread of plastics, the release of carbon. They show that our actions are not ephemeral, They will persist, written into the geological record, shaping the planet long after we are gone. This realization can be sobering, but it is also empowering. It means that what we do matters, not just now, but for millennia. It means that we have the power to shape the story the future will read in the sediments we leave behind. All of these lessons, resilience, interconnection, time, limits, humility, hiddenness, continuity, converge on a deeper truth, that the planet is not a collection of separate parts, but a single, dynamic system. The deep ocean is not just a destination for exploration or a source of resources. It is a vital part of the machinery that makes Earth habitable. It regulates climate, recycles nutrients, stores carbon, supports biodiversity, and records the planet's history. It is connected to the atmosphere, the continents, and the biosphere in ways that are complex and profound. And it is shaped by the same forces that shape us, and in turn shapes the conditions that make our existence possible. This understanding carries both warning and hope. The warning is that our actions can disrupt this system in ways that have far-reaching consequences. The hope is that by understanding the system, we can act in ways that sustain it. The deep teaches us that complexity is not chaos, that even the most intricate systems follow patterns and principles we can learn. It shows us that small actions can have large effects, both destructive and constructive. And it suggests that by aligning our actions with the rhythms and limits of the planet, we can build a future that is not only sustainable but thriving. It also teaches us about wonder. For all its darkness and pressure, Milwaukee Deep is a place of astonishing beauty and complexity. It is home to organisms that defy imagination, processes that operate on scales we struggle to comprehend, and records that reach back into deep time. It challenges our assumptions, expands our horizons, and reminds us of how much we have yet to learn. Wonder is not a trivial emotion. It is the root of curiosity, the spark that drives exploration and discovery. It is what pushes us to send instruments into the depths, to analyze sediments grain by grain, to decode the signals that rise from the abyss. And it is what inspires us to care, to see the deep not just as a scientific subject but as a part of the world worth protecting. The abyss, in the end, is a teacher that does not speak loudly. Its lessons are quiet, written in slow processes and subtle signals. They require patience to uncover and humility to understand. But they are among the most important lessons we can learn, about how life endures, how systems connect, how time unfolds, how limits matter, how small things shape great ones. They remind us that we're part of a larger whole, that our actions have consequences, and that our future is bound up with the health of the systems that sustain us. And as we absorb these lessons, we begin to see the abyss not just as a place to study, but as a mirror, one that reflects both the power and the fragility of life, both the vastness of Earth's history and the immediacy of our choices. It shows us where we have been, where we are, and where we might go. And it leads us naturally into the final layer of this journey, the stillness at the bottom of the world, the quiet that holds everything together, the place where time, history, and mystery converge in a silence that is anything but empty. If you are somehow able to descend all the way to the floor of Milwaukee Deep and rest there, 9 kilometers beneath the surface of the Atlantic, the first thing you might notice is how profoundly still it feels. Not silent, because the deep ocean is never truly silent. There are always faint tremors from distant earthquakes, the soft movement of water, the minute crackling of biological activity, but still in a way that has no counterpart on land. Here, movement is slow and rare, light is absent, the water is cold and dense, and the weight of the ocean above presses with a steady, relentless force. It is a world that seems, at first glance, untouched by time. Yet this stillness is not emptiness. It is the product of balance, of countless processes interacting in ways that stabilize and sustain one another. It is a stillness that holds the memory of the past, the reality of the present, and the potential of the future all at once. This is the nature of the hadal world. It is not lifeless or static, but governed by rhythms that unfold on scales far beyond our usual perception. A particle of marine snow takes weeks to sink from the surface to this depth. But once it settles into the sediment, it may remain there for thousands or even millions of years. A current that seems imperceptible to us might slowly transport water from one part of the ocean to another over centuries. Even the movements of tectonic plates which shape the trench itself occur so gradually that they are almost frozen from our perspective. What feels like stillness is in fact motion, at a pace too slow for us to perceive. Motion that shapes the landscape, drives the cycles of chemistry, and sustains the ecosystems that exist here. This deep stillness teaches us something fundamental about how the planet works. Much of Earth's activity is invisible, not because it is absent, but because it happens on timescales and in ways that our senses are not tuned to detect. The same is true of the processes unfolding here. The sediments beneath Milwaukee Deep are constantly accumulating grain by grain as particles drift down from the surface. Microbial communities are constantly metabolizing, breaking down organic matter and transforming chemicals in ways that influence the global cycles of carbon, nitrogen, and sulfur. Currents are constantly circulating, distributing heat, oxygen, and nutrients. Even the trench itself is changing, as tectonic plates converge and the seafloor is slowly drawn downward into the Earth's mantle. All of this is happening, always. It is just that the pace is so slow, the change is so subtle, that from the perspective of a human lifetime it appears unchanging. Understanding this stillness requires a shift in perspective. We are accustomed to thinking of motion as something obvious. Waves crashing on a shore, wind rustling through trees, clouds racing across the sky. But in the deep ocean, motion often means the slow drift of water molecules, the gradual burial of sediments, the imperceptible migration of elements through chemical reactions. These processes may be invisible, but they are powerful. They shape the physical structure of the ocean basins, regulate the chemistry of the water, and sustain the ecosystems that depend on them. They also connect the deep to the rest of the planet. The water that circulates through Milwaukee Deep eventually surfaces in distant regions, influencing climate and weather. The carbon that is buried in its sediments affects the composition of the atmosphere. The tectonic activity that shapes the trench drives the formation of mountains and continents elsewhere. The stillness of the deep is not isolation, it is integration, the slow heartbeat of a system that spans the entire planet. This stillness also has a profound effect on the life that exists here. In an environment where change is slow and resources are scarce, organisms have evolved strategies that emphasize stability and endurance over speed. Growth is measured not in weeks or months, but in decades. Some deep-sea corals and sponges can live for centuries or even millennia, their growth rings recording changes in the ocean over timescales that dwarf human history. Fish like the grenadier and the snailfish grow slowly, reproduce infrequently, and live long lives. Microbial communities may persist for thousands of years, their composition changing little over time. This stability is not stagnation, but adaptation, a way of thriving in a world where rapid change is rare and often catastrophic. The stillness of the deep is not without activity, it is simply activity of a different kind. Instead of bursts of growth followed by die-offs, there is steady persistence. Instead of dramatic migrations, there is patient waiting. Instead of the boom and bust cycles common in surface ecosystems, there are long, slow arcs of change. These dynamics have implications far beyond the deep ocean. They show us that stability does not mean absence of change, and that resilience does not require constant motion. They suggest that systems can be dynamic and productive, even when they appear still, and that endurance can be as powerful a strategy as speed. There is another layer to this stillness, one that speaks not just to biology and geology, but to time itself. Down here, time seems to lose its usual meaning. A second or a minute is irrelevant in a place where processes unfold over centuries. Even a human lifetime is a fleeting moment. The trench has existed for millions of years. The sediments at its base contain records that stretch back far beyond the dawn of our species. The water that fills it may have last seen the surface before the rise of agriculture or the fall of empires. To contemplate this is to be reminded of how brief our time is and how long the Earth's story has been unfolding without us. This sense of deep time can be unsettling. It reminds us that we are small, that our civilizations are recent, that the systems we depend on have been operating for eons before we arrived and will continue long after we're gone. But it can also be grounding. It shows us that the world is larger than our immediate concerns, that there are processes and patterns that endure beyond the rise and fall of societies. It reminds us that the changes we make today, the carbon we release, the pollutants we spread, the species we endanger, will persist long after us, recorded in the sediments of places like Milwaukee Deep. It challenges us to think not just in terms of years or decades, but in terms of centuries and millennia, to consider the legacy we are leaving for a future we will never see. The stillness at the bottom of the world also has a contemplative quality. It invites reflection, not in a mystical or poetic sense, but in the sense of perspective. Standing figuratively at the bottom of Milwaukee Deep, it is hard not to think about the scale of the systems we are part of, the complexity of the interactions that sustain them, and the fragility of the balance that makes life possible. The abyss strips away the noise and distraction of the surface, leaving only the fundamental questions. How do we fit into this system? What responsibilities do we have toward it? What does it mean to live on a planet where processes we cannot control, and often cannot even perceive, determine the conditions of our existence? These are not abstract questions. They are practical ones. Our survival depends on the stability of systems that operate far beyond our daily experience. The deep ocean regulates climate by storing carbon and redistributing heat. It recycles nutrients that sustain life throughout the marine food web. It buffers the effects of atmospheric changes and absorbs the excess heat generated by human activity. These functions depend on the slow, steady processes that unfold in places like Milwaukee Deep. If we disrupt them by warming the planet too quickly, by polluting the ocean, by destabilizing circulation patterns, we risk destabilizing the systems that make Earth habitable. The stillness of the deep is not just a curiosity, it is a foundation, one that we rely on even if we rarely think about it. The abyss also offers a lesson in patience. The changes that occur here cannot be rushed. They follow their own rhythms dictated by physics, chemistry, and biology. No amount of human urgency can speed up the accumulation of sediments or the circulation of deep water. No policy or technology can shorten the timescales on which tectonic plates move or microbial communities evolve. This is a hard lesson for a species accustomed to rapid change, to technologies that transform our lives in decades, and policies that shift with each election. It reminds us that some problems cannot be solved quickly, that some processes cannot be forced. It challenges us to think in longer terms, to plan not just for the next year or decade, but for the next century or millennium. Patience, however, does not mean passivity. The deep shows us that slow processes can have profound effects, and that small changes accumulated over time can reshape the world. A few millimeters of sediment deposited each millennium eventually become kilometers of rock. The slow movement of tectonic plates builds mountains and opens oceans. The gradual burial of carbon in sediments regulates the climate over millions of years. This perspective is both sobering and hopeful. It suggests that the damage we do to the planet may take centuries to repair, but it also suggests that deliberate, sustained action, even if it seems small, can have lasting impact. It encourages us to think beyond immediate results and to invest in actions whose benefits may not be visible for generations. The stillness of the deep also underscores the importance of balance. The systems that operate here are finely tuned, the result of millions of years of interaction between geology, chemistry, and biology. Disturbances can reverberate through the system in unexpected ways. A change in temperature can alter the solubility of gases, which affects microbial metabolism, which in turn influences carbon storage and nutrient cycling. A shift in circulation can change oxygen levels, reshaping communities of organisms and altering chemical gradients. These changes are not isolated. They cascade through the system, often with consequences far beyond their point of origin. Understanding this teaches us that balance is not a static state but a dynamic one, maintained through constant adjustment and feedback. It also shows us that disrupting one part of a system can have consequences for the whole. This has direct implications for how we approach environmental challenges. It suggests that solutions must be systemic, addressing the root causes of problems rather than their symptoms. It warns us that interventions in one part of the system can have unintended consequences elsewhere. And it reminds us that maintaining balance requires constant attention and care. The deep ocean does not stay stable on its own. Its stability is the result of interactions between countless processes operating at different scales. The same is true of the Earth system as a whole. If we want to sustain the conditions that make life possible, we must pay attention to those interactions and act with an understanding of their complexity. The stillness at the bottom of Milwaukee Deep is also a reminder of how much remains unknown. For all our technology and exploration, we have only scratched the surface of what there is to learn. Most of the species that live here have not been described. Many of the chemical and biological processes that shape this environment are poorly understood. The interactions between geological activity, microbial metabolism, and global climate remain subjects of active research. Even basic questions, such as how deep ocean ecosystems will respond to continued warming, acidification and pollution, do not yet have clear answers. This ignorance is not a failure but an invitation. It shows us that discovery is still possible, that mystery still exists, that there is still much to learn about the planet we call home. It also suggests that humility is essential. The more we learn about the deep, the more we realize how much we do not know. The systems here are complex beyond our current understanding, and our attempts to manipulate them can have consequences we did not anticipate. Humility does not mean inaction, but it does mean caution, a recognition that our knowledge is limited and that we should act with care when dealing with systems we do not fully understand. It also means valuing the unknown not as a gap to be filled, but as a space of possibility, a reminder that the world is larger and more complex than our models and theories can capture. Perhaps the most profound lesson of the stillness at the bottom of the world is about perspective. From the surface, our concerns can seem all-consuming. We worry about economies, politics, technologies, and conflicts. We measure success in years or decades. But from the vantage point of Milwaukee Deep, these concerns shrink. They become brief flashes against a backdrop of processes that unfold over millennia. This does not make them unimportant. It simply places them in context. It shows us that the systems that sustain life are vast and enduring, that they operate on scales far beyond our immediate experience, and that our actions are part of a story much larger than ourselves. This perspective can change how we think and act. It can temper our arrogance and deepen our sense of responsibility. It can encourage us to look beyond short-term gains and consider the long-term consequences of our choices. It can inspire us to align our actions with the rhythms of the planet rather than working against them. And it can remind us that our future is inseparable from the health of the systems that sustain us. The stillness of the deep is not an absence of life or change. It is the foundation upon which life and change occur. It is the canvas on which the history of the planet is written, the stage on which its dramas unfold. It is a reminder that beneath the surface, beneath the waves and weather, beneath the noise and activity of human civilization, there is a deeper world, one that operates on its own terms and according to its own rhythms. It is a world that sustains us even as we alter it, that records our actions even as it shapes them, that endures even as we come and go. And as we contemplate this stillness, we might find in it not just knowledge but wisdom, the wisdom to act with patience and humility, the wisdom to recognize our place in a system larger than ourselves, the wisdom to see connection where we once saw separation and continuity where we once saw isolation, the wisdom to understand that our actions today will echo in the sediments of tomorrow, and that the choices we make will shape not only our future, but the future of the planet itself. The trench will remain, long after our cities have crumbled and our technologies have become relics. The sediments will continue to accumulate, the microbes will continue to metabolize, the water will continue to circulate, the stillness at the bottom of the world will endure, indifferent to our presence and yet shaped by it, a silent witness to the story of a planet that is always changing and always the same. And in that stillness, if we are willing to listen, we can hear the faint but unmistakable rhythms of the earth itself, slow, steady and patient, guiding us toward an understanding of where we come from, what sustains us, and where we might go next.